black holes are among the most fascinating and terrifying phenomena in the universe. These regions of space have gravity so intense that nothing, not even light, can escape once it crosses the event horizon. At the center of a black hole lies a singularity, a point of infinite density where the laws of physics as we know them break down. Black holes can form from the remnants of massive stars after they collapse under their own gravity, but some, known as supermassive black holes, sit at the centers of galaxies and have masses millions or even billions of times that of the Sun. The Milky Way's supermassive black hole, Sagittarius A, has a mass equivalent to 4 million suns and plays a crucial role in anchoring our galaxy. But black holes aren't just destructive, they also contribute to the formation and evolution of galaxies, influencing their structure and dynamics. Black holes are the universe's ultimate enigmas, regions where gravity becomes so intense that not even light can escape. They form when massive stars exhaust their nuclear fuel and collapse under their own gravity, creating a singularity, a point of infinite density where the known laws of physics break down. These singularities are surrounded by an event horizon, a boundary beyond which nothing can return. To an outside observer, time appears to stop at the event horizon, making black holes not just objects but places where space and time behave in ways we can barely comprehend. But not all black holes are created equal. Stellar black holes, with masses a few times that of the Sun, are born from collapsing stars, while supermassive black holes, with masses millions or billions of times greater, lurk at the centers of galaxies. How these supermassive black holes form remains one of the great mysteries of astrophysics. Some theories suggest they grew by consuming vast amounts of matter over billions of years, while others propose they formed directly from the collapse of massive primordial clouds of gas in the early universe. One of the most fascinating aspects of black holes is their interaction with their surroundings. As matter falls toward a black hole, it forms an accretion disk, heating up and emitting intense radiation. This process can generate powerful jets of particles, shooting out at nearly the speed of light and spanning thousands of light years. These jets can influence the formation of stars and even entire galaxies, making black holes not just destroyers but also creators in the cosmic ecosystem. Perhaps the most tantalizing question about black holes is what lies beyond their event horizons. Could they be portals to other regions of space or even other universes? Some theoretical models suggest that black holes might be connected to white holes' hypothetical counterparts that expel matter instead of absorbing it through wormholes. While these ideas remain speculative, they fuel our curiosity about the possibilities of space-time and the boundaries of our physical understanding. Black holes are also laboratories for studying extreme physics. The conditions near a black hole's event horizon challenge both general relativity and quantum mechanics, offering a unique testing ground for theories of quantum gravity. The detection of gravitational waves from merging black holes, first observed in 2015, has opened a new window into these phenomena, providing insights into their properties and evolution. In the end, black holes are not just cosmic oddities, they are central to our understanding of the universe. They influence the formation of galaxies, shape the flow of matter, and push the boundaries of physics. As we continue to study them, we edge closer to answering some of the most profound questions about the nature of space, time, and the universe itself. Exoplanets, the quest for Earth's twins. Exoplanets, or planets beyond our solar system, are among the most exciting discoveries in modern astronomy. Since the first confirmed detection in 1992, over 5,000 exoplanets have been identified, revealing a dazzling array of worlds. From scorching hot gas giants orbiting perilously close to their stars to icy, rocky planets on the fringes of their systems, the diversity of exoplanets has reshaped our understanding of planetary formation and the potential for life elsewhere in the universe. One of the most sought-after goals in exoplanet research is finding Earth-like planets in the habitable zone of their stars. The habitable zone, often called the Goldilocks zone, is the region around a star where conditions might allow liquid water to exist on a planet's surface. Planets in this zone are prime candidates for hosting life as we know it. Among the most promising discoveries is Proxima Centauri b, an Earth-sized planet orbiting the closest star to our solar system. Located just over 4 light-years away, Proxima b lies within its star's habitable zone, though its habitability is still under debate due to its star's intense radiation. The discovery of super-Earths, planets larger than Earth but smaller than Neptune, has expanded our understanding of planetary types. These worlds, which have no analog in our solar system, could have thick atmospheres or vast oceans, providing unique environments for life. Similarly, mini-Neptunes, with sizes and compositions between those of Earth and Neptune, challenge existing models of planet formation, suggesting that planetary diversity is far greater than we imagined.
The search for exoplanets has also led to groundbreaking technologies and methods. The transit method, which measures the dimming of a star's light as a planet crosses in front of it, has been particularly successful. Observatories like Kepler and TESS have used this technique to identify thousands of exoplanets. Meanwhile, direct imaging and spectroscopic analysis of exoplanet atmospheres are opening new frontiers, allowing scientists to study the chemical compositions of distant worlds and search for signs of life.
The James Webb Space Telescope is poised to revolutionize exoplanet research, with its ability to analyze the atmospheres of Earth like planets in unprecedented detail. By detecting molecules such as water vapor, oxygen, and methane, Webb may provide the first evidence of life on an exoplanet, answering one of humanity's most profound questions: are we alone in the universe? Exoplanets remind us of the vast potential for life and the endless possibilities for exploration. Each discovery brings us closer to understanding the conditions required for life and the place of Earth in the cosmic tapestry. As we continue to explore these distant worlds, we not only learn about their nature but also gain a deeper appreciation for the uniqueness and fragility of our own planet. The birth of stars, forging light in the darkness, expanded. Stars are born in the vast, cold regions of space known as molecular clouds or nebulae. These interstellar nurseries, composed primarily of hydrogen and helium, are often enriched with traces of heavier elements from previous generations of stars. Spanning dozens to hundreds of light years across, these clouds are dynamic regions where gravity, turbulence, and magnetism interact in complex ways. The process of star formation begins when a triggering event, such as the shock wave from a nearby supernova or the gravitational interaction of passing galaxies, compresses parts of a molecular cloud. As the cloud collapses under its own gravity, it fragments into smaller clumps, each potentially forming one or more stars. These dense clumps, known as prestellar cores, continue to contract, increasing in density and temperature. Within these cores, gas molecules collide more frequently, and the rising pressure creates a central protostar, a hot, dense object that represents the early stage of stellar birth. During this phase, the protostar is surrounded by a rotating disk of gas and dust, which will later play a role in forming planets, moons, and other celestial bodies. The protostar's evolution is a race against time. If the core accumulates enough mass and the temperature at its center reaches around 10 million Kelvin, nuclear fusion ignites. This process converts hydrogen into helium, releasing enormous amounts of energy in the form of light and heat. The ignition of fusion halts further gravitational collapse, establishing hydrostatic equilibrium, a balance between the inward pull of gravity and the outward pressure of radiation. At this moment, a star is officially born. The fate of a star depends on its mass. Low-mass stars like red dwarfs burn their hydrogen fuel slowly, living for tens of years far longer than the current age of the universe. Stars like our Sun, categorized as medium-mass stars, live for about 10 billion years, providing a stable environment for planets and potential life. Massive stars, on the other hand, are short-lived cosmic giants. Burning their fuel at an astonishing rate, they shine brilliantly for a few million years before exploding as supernovae, scattering heavy elements into space and leaving behind neutron stars or black holes. Star formation is not a solitary process but a communal one. Many stars form in clusters, with hundreds or even thousands of stars emerging from the same molecular cloud. These stellar siblings are bound by gravity and can remain loosely associated for millions of years before dispersing. Some clusters, like the Pleiades, remain visible long after their stars have matured, serving as markers of their common origin. The importance of star formation extends beyond the creation of stars themselves. Stars are the universe's primary factories for producing heavier elements through nuclear fusion. Elements like carbon, oxygen, and nitrogen, the building blocks of life, are forged in the hearts of stars and released into space during their later stages. Without star formation, the universe would lack the diversity of elements needed for planets, ecosystems, and even human existence. Star formation is a process of both creation and transformation. It turns simple clouds of gas into luminous beacons that light up the universe, driving the cycles of matter and energy that shape galaxies. It's a reminder of the universe's capacity for renewal, as each generation of stars builds on the legacy of those that came before. Through the birth of stars, the cosmos continuously evolves, creating the conditions necessary for complexity, diversity, and life. The evolution of stars, life cycles on a cosmic scale. Stars, like all things in the universe, have life cycles dictated by their initial mass and composition. From their fiery beginnings to their often dramatic ends, stars undergo transformations that span millions to billions of years, shaping the very fabric of galaxies and contributing to the cosmic ecosystem. Understanding these life cycles provides insight into the forces that govern the universe and the origins of the elements that make up everything we see. Low-mass stars, which include red dwarfs, have relatively simple and prolonged life cycles. These stars burn hydrogen in their cores at a slow pace, allowing them to shine for tens of billions of years, far outliving stars like the Sun. As they exhaust their hydrogen fuel, they eventually shrink and cool, becoming white dwarfs. These remnants will slowly radiate away their remaining heat over trillions of years, eventually fading into cold, dark black dwarfs. Medium-mass stars, like the Sun, follow a more complex path. After spending billions of years in a stable phase, converting hydrogen into helium in their cores, they eventually run out of hydrogen. Without the pressure from nuclear fusion to counteract gravity, the core contracts while the outer layers expand, transforming the star into a red giant. During this phase, the star begins fusing helium into heavier elements like carbon and oxygen. However, once the core runs out of fusible material, the outer layers are ejected, forming a planetary nebula, while the core remains as a white dwarf. Massive stars, which start their lives with at least 8 times the Sun's mass, live fast and die young. These stars burn through their nuclear fuel in just a few million years, reaching temperatures and pressures that allow them to create elements as heavy as iron through fusion. When the core can no longer sustain fusion, it collapses under its own gravity, triggering a supernova explosion. This cataclysmic event releases enormous amounts of energy and disperses heavy elements into space, enriching the interstellar medium and seeding future generations of stars. The remnants of massive stars depend on their mass. Stars that are moderately massive may leave behind neutron stars, ultra-dense objects composed almost entirely of neutrons. These neutron stars often rotate rapidly and emit beams of radiation, becoming pulsars. For the most massive stars, the core collapse forms a black hole, an object so dense that not even light can escape its gravitational pull. The life cycle of a star is not just a story of birth and death, but a process of cosmic recycling. The material ejected by dying stars enriches the surrounding space, creating the raw ingredients for new stars, planets, and life. This cycle of stellar evolution ensures that the universe remains dynamic and ever-changing, a continuous interplay of creation and destruction that drives cosmic evolution. Through the study of stars, we learn about the origins of the elements that make up our world, the forces that shape galaxies, and the processes that have been at work since the universe's beginning. Each star, no matter its size, contributes to the grand narrative of the cosmos, leaving behind a legacy that endures for eons. Galactic collisions, the cosmic dance of destruction and creation. Galactic collisions are among the most dramatic and transformative events in the universe, shaping the structure and evolution of galaxies over billions of years. While the term collision evokes images of catastrophic impacts, in reality, these cosmic encounters are more akin to a slow-motion dance. Galaxies, composed mostly of empty space between stars, pass through and around each other over millions or billions of years, with stars rarely colliding directly. Instead, gravitational forces reshape galaxies, triggering bursts of star formation, altering their shapes, and sometimes merging them into entirely new entities. The Milky Way itself is no stranger to this cosmic choreography. Our galaxy is currently on a slow collision course with the Andromeda Galaxy, the largest member of the local group. In about 4.5 billion years, these two giant galaxies will begin to merge, creating a new, larger galaxy often referred to as Milkomeda. This future collision will radically reshape both galaxies, stretching their stars into tidal streams and forming a new galactic nucleus. Despite the scale of this event, our solar system is unlikely to be affected directly, though the night sky would be filled with dazzling displays of stars and gas. Collisions between galaxies are not rare. In fact, they are an essential part of galactic evolution. Smaller galaxies are often absorbed by larger ones in events known as galactic cannibalism. The Milky Way has already consumed several smaller galaxies, including the Sagittarius dwarf galaxy and the Magellanic Clouds. These interactions leave behind stellar streams, trails of stars stripped from the smaller galaxy that can be traced across the sky. These streams are crucial for understanding the Milky Way's history and its interactions with neighboring galaxies. One of the most striking examples of a galactic collision is the Antennae galaxies, located about 45 million light-years away in the constellation Corvus. These two galaxies are in the process of merging, their gravitational interactions triggering intense bursts of star formation. Vast clouds of gas and dust collide, compressing and igniting into new stars. The Antennae galaxies offer a glimpse into the future of the Milky Way and Andromeda, showcasing the creative potential of galactic mergers. Galactic collisions also have profound effects on supermassive black holes at the centers of galaxies. As galaxies merge, their central black holes are drawn toward each other, eventually forming a binary system. Over time, these black holes may merge, releasing powerful gravitational waves. Observing these events provides insights into the dynamics of black holes and the role they play in shaping galaxies. The role of dark matter in galactic collisions cannot be overstated. While stars and gas interact visibly, the invisible halos of dark matter surrounding galaxies dictate the overall dynamics of the encounter. Simulations of galactic collisions, such as those performed by the Illustris and Eagle projects, reveal how dark matter shapes the resulting structures and influences star formation. These models show that dark matter acts as a stabilizing force, helping merged galaxies settle into new configurations. Ultimately, galactic collisions are not just destructive events, they are processes of renewal and transformation. They recycle gas and dust, create new generations of stars, and reshape galaxies into new forms. These interactions remind us that the universe is a dynamic, ever-changing environment where creation and destruction go hand in hand, contributing to the rich tapestry of cosmic evolution. Gravitational waves, ripples in the fabric of space-time. Gravitational waves are ripples in space-time caused by some of the most energetic events in the universe. Predicted by Albert Einstein in 1916 as part of his general theory of relativity, these waves remained undetected for nearly a century. It wasn't until 2015 that scientists made the first direct observation of gravitational waves using the Laser Interferometer Gravitational Wave Observatory, LIGO. This groundbreaking discovery confirmed Einstein's prediction and opened an entirely new way of observing the cosmos. Gravitational waves are produced when massive objects accelerate, such as during the collision of two black holes or the merger of neutron stars. These waves travel at the speed of light, stretching and compressing space-time as they pass. While their effects on Earth are minuscule, changing distances by less than the width of a proton, advanced detectors like LIGO and Virgo can measure these tiny distortions with remarkable precision. The first detected gravitational wave event, GU 15914, came from the merger of two black holes approximately 1.3 billion light-years away. This collision released more energy in gravitational waves than the combined light of all the stars in the observable universe during the event. Subsequent detections have revealed a variety of cosmic phenomena, including neutron star mergers, which produce both gravitational waves and electromagnetic signals like gamma-ray bursts. These multi-messenger observations provide a more comprehensive picture of these events, allowing scientists to study them in unprecedented detail. Gravitational waves have also provided new insights into the population of black holes in the universe. Before LIGO's discoveries, astronomers had little evidence of black holes in the 30 to 50 solar mass range. The detection of such objects has reshaped our understanding of how black holes form and evolve, particularly in binary systems. These observations have also challenged models of stellar evolution, as they suggest that certain environments, such as dense star clusters, may produce black holes more efficiently than previously thought. The study of gravitational waves extends beyond black holes and neutron stars. Scientists hope to detect waves from other phenomena, such as the rotation of rapidly spinning neutron stars, pulsars, the collapse of massive stars into black holes, or even primordial gravitational waves from the early universe. Detecting these signals could provide insights into the conditions immediately following the Big Bang, shedding light on cosmic inflation and the origins of the universe. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna, LISA, will expand our reach into the cosmos. Operating in space, LISA will detect lower-frequency waves, allowing scientists to study supermassive black hole mergers and other large-scale phenomena. Additionally, the discovery of gravitational waves has implications for understanding dark matter and quantum gravity, as these signals provide a unique perspective on the interplay between gravity and the quantum realm. Gravitational waves remind us that the universe is dynamic and ever-changing. They reveal the invisible motions of the cosmos, offering a way to listen to events that would otherwise remain hidden. Through their study, we gain a deeper understanding of the forces that shape the universe, pushing the boundaries of human knowledge and opening new frontiers in astronomy and physics. Dark matter and dark energy, the invisible forces shaping the universe. Dark matter and dark energy are two of the most enigmatic components of the universe, making up approximately 95% of its total mass energy content. Despite their profound influence, they remain largely invisible and poorly understood, challenging our understanding of the cosmos and the fundamental laws of physics. Together, they govern the behavior of galaxies, the structure of the universe, and its ultimate fate. Dark matter, which constitutes about 27% of the universe, does not emit, absorb, or reflect light, making it undetectable through traditional telescopes. Its presence is inferred through its gravitational effects on visible matter, such as stars and galaxies. Observations of galaxy rotation curves, gravitational lensing, and the large-scale structure of the universe provide compelling evidence for dark matter's existence. Without it, galaxies would not have enough mass to remain gravitationally bound, and the cosmic web would not have formed as we observe it today. Dark energy, on the other hand, makes up a staggering 68% of the universe and is responsible for its accelerated expansion. Discovered in the late 1990s through studies of distant supernovae, dark energy appears to counteract gravity, driving galaxies apart at an increasing rate. While its exact nature remains unknown, some theories suggest it is a property of space itself, while others propose it may be a dynamic field or an entirely new force of nature. The interplay between dark matter and dark energy shapes the evolution of the universe. Dark matter provides the gravitational framework for galaxy formation, while dark energy determines the large-scale behavior of the cosmos. Together, they influence the distribution of matter, the growth of cosmic structures, and the fate of the universe. If dark energy continues to dominate, the universe could end in a big freeze or a big rip, where all matter is torn apart by the accelerating expansion. Understanding dark matter and dark energy is one of the greatest challenges in modern physics. Experiments such as those at the Large Hadron Collider, as well as dedicated dark matter detectors like Xenon 1T, are searching for evidence of dark matter particles. Meanwhile, surveys like the Dark Energy Survey and upcoming missions like the Euclid Space Telescope aim to uncover the properties of dark energy by mapping the distribution of galaxies in the cosmic web. These mysterious forces remind us that the universe is far more complex than it appears. They challenge our assumptions about matter, energy, and the nature of reality, pushing us to explore the unknown. Through the study of dark matter and dark energy, we hope to uncover the hidden architecture of the cosmos and gain a deeper understanding of the forces that govern its past, present, and future. The Big Bang, the birth of space and time. The Big Bang is not just a theory about the origin of the universe. It's a window into the very beginning of space, time, and matter as we know it. Approximately 13.8 billion years ago, the universe emerged from an incredibly hot, dense state. Contrary to the imagery of an explosion, the Big Bang was a rapid expansion of space itself, creating the framework within which galaxies, stars, and planets would later form. In the earliest moments of the universe, conditions were so extreme that the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were unified. This state, known as the Planck epoch, lasted less than a trillionth of a second, after which these forces began to separate. During this time, the universe underwent rapid inflation, expanding exponentially in a fraction of a second. Inflation smoothed out irregularities, laying the groundwork for the large-scale structure of the cosmos. As the universe cooled, particles like quarks and gluons emerged, combining to form protons and neutrons. Within minutes, these particles fused to create the nuclei of hydrogen, helium, and trace amounts of lithium, in a process called nucleosynthesis. For the next 380,000 years, the universe remained a seething plasma of charged particles, preventing light from traveling freely. It wasn't until the formation of neutral atoms, when electrons bonded with nuclei, that the universe became transparent, allowing light to travel across vast distances. This light is now observed as the cosmic microwave background, CMB, a faint glow that provides a snapshot of the infant universe. The CMB is one of the most important pieces of evidence for the Big Bang theory. Its uniformity, with subtle fluctuations, reveals the density variations that seeded the formation of galaxies and clusters. Observations of the CMB by missions like Planck and MAP have provided critical insights into the universe's age, composition, and rate of expansion. While the Big Bang marks the beginning of the observable universe, questions remain about what, if anything, existed before it. Some theories propose that the Big Bang was one event in a cycle of cosmic expansion and contraction, while others suggest it could have arisen from quantum fluctuations in a pre-existing multiverse. These ideas remain speculative, but they underscore the profound mystery of the universe's origins. The story of the Big Bang is not just about the past, it is deeply connected to the present and future. The same processes that shaped the early universe continue to influence its evolution, from the formation of stars and galaxies to the mysterious forces of dark matter and dark energy. Understanding the Big Bang brings us closer to answering fundamental questions about the nature of existence and our place in the cosmos. The end of the universe. Scenarios for cosmic fate. While the universe began with the Big Bang, its ultimate fate remains one of the greatest mysteries of modern science. The destiny of the cosmos depends on the interplay between dark energy, dark matter, and gravity. Several scenarios have been proposed for how the universe might evolve, each reflecting the balance of these forces and the underlying structure of space-time. One possibility is the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy continues to drive the accelerated expansion of the universe indefinitely. Over time, galaxies will drift farther apart, making it increasingly difficult for light or matter to interact. Stars will exhaust their nuclear fuel and die, leaving behind black holes, neutron stars, and white dwarfs. Eventually, even these remnants will decay, and the universe will become a cold, dark expanse filled with diffuse particles and radiation. Another scenario is the Big Crunch, where the expansion of the universe reverses due to the gravitational pull of matter. In this case, the universe would contract over billions of years, with galaxies, stars, and eventually all matter collapsing into a dense, hot state similar to the conditions of the Big Bang. This cyclical model suggests that the universe could undergo endless cycles of expansion and contraction, potentially giving rise to new Big Bangs and universes. The Big Rip offers a more dramatic end. If dark energy's influence increases over time, it could overpower all other forces, including gravity. In this scenario, galaxies would be torn apart, followed by stars, planets, and even atoms, as the very fabric of space-time is ripped apart. The Big Rip represents the ultimate triumph of dark energy, where the universe disintegrates into its most fundamental components. Some theories propose that the universe could experience a vacuum decay, a catastrophic event triggered by a quantum fluctuation. If our universe exists in a false vacuum state, it could eventually transition to a lower energy true vacuum state. This transition would propagate at the speed of light, obliterating everything in its path and creating an entirely new universe with different physical laws. Observations of dark energy and the rate of cosmic expansion suggest that the universe is most likely headed toward a big freeze. However, our understanding of dark energy is still incomplete, leaving room for alternative possibilities. Future observations, such as improved measurements of the Hubble constant and dark energy, may provide critical insights into the universe's ultimate fate. The end of the universe is a humbling and thought-provoking concept. It reminds us of the impermanence of cosmic structures and the transience of existence. While the universe's fate lies billions or even trillions of years in the future, contemplating its destiny helps us appreciate the fleeting beauty of the present and the extraordinary processes that have shaped the cosmos we inhabit. Time and relativity, the flexible nature of reality. Time, one of the most fundamental aspects of human experience, is not as rigid as it seems. Albert Einstein's theory of relativity revolutionized our understanding of time, revealing that it is a flexible dimension that can stretch, shrink, and even stop under certain conditions. Time is deeply intertwined with space, forming the fabric of space-time, which is influenced by gravity and motion. In Einstein's special theory of relativity, time dilation occurs when objects move close to the speed of light. As an object's velocity increases, time for that object slows relative to an outside observer. For example, astronauts traveling at near light speed would experience time more slowly than people on Earth. This phenomenon has been confirmed through experiments involving atomic clocks on high-speed aircraft and satellites, demonstrating that time is not absolute but relative. General relativity adds another layer of complexity, showing that gravity can also warp time. Near massive objects like black holes, the intense gravitational field stretches space-time, causing time to pass more slowly. This effect, known as gravitational time dilation, means that an observer near a black hole would experience time more slowly than someone farther away. In extreme cases, such as near the event horizon of a black hole, time could appear to stop entirely from the perspective of a distant observer. Relativity challenges our intuitive understanding of time and space, suggesting that the sequence of events can vary depending on an observer's frame of reference. This concept is crucial for understanding the structure of the universe, from the expansion of space to the behavior of light and matter in extreme environments. It also has practical applications, such as in the functioning of GPS systems, which account for relativistic time effects to provide accurate location data. The study of time extends beyond relativity into the realms of quantum mechanics and cosmology. Some theories suggest that time may not be fundamental but emergent, arising from deeper physical principles. Others propose that the flow of time could reverse in certain conditions, or that multiple timelines could coexist within a multiverse. These ideas, while speculative, highlight the complexity of time as a concept and its central role in the fabric of reality. Time is not just a scientific phenomenon, but a philosophical one, raising questions about causality, free will, and the nature of existence. Is time a river flowing in one direction? Or is it a landscape where all moments exist simultaneously? These questions remind us that our understanding of time, like the universe itself, is a work in progress, shaped by discoveries yet to come. The life cycle of galaxies, from birth to transformation. Galaxies are the building blocks of the universe, vast collections of stars, gas, dust, and dark matter bound together by gravity. Each galaxy tells a story of cosmic evolution, from its birth in the early universe to its transformation through interactions and internal processes. The life cycle of galaxies spans billions of years, shaped by both internal dynamics and external influences. The story of a galaxy begins with the formation of massive clouds of hydrogen and helium in the aftermath of the Big Bang. In the early universe, these clouds collapsed under the force of gravity, forming the first stars. These primordial stars were massive and short-lived, producing the first heavy elements through nuclear fusion and supernova explosions. These elements seeded the surrounding gas, setting the stage for the formation of more complex structures. Galaxies formed as regions of higher density in the cosmic web pulled in surrounding matter. These proto-galaxies were small and irregular, often colliding and merging to form larger systems. Over billions of years, these mergers created the diverse types of galaxies we see today: spirals, ellipticals, and irregulars. Spiral galaxies, like the Milky Way, are characterized by their flat, rotating disks and well-defined spiral arms. Elliptical galaxies, on the other hand, are more spherical or elongated and often contain older, redder stars. Irregular galaxies defy categorization, with chaotic shapes resulting from gravitational interactions or mergers. Galaxies are not isolated entities, they interact with their surroundings and each other in complex ways. Gravitational interactions between galaxies can trigger dramatic transformations. For example, when galaxies collide, their stars rarely collide directly due to the vast distances between them. However, their gas and dust clouds do interact, leading to intense bursts of star formation known as starbursts. Over time, the merging galaxies may settle into a new configuration, often forming an elliptical galaxy. The Milky Way itself is a dynamic and evolving galaxy. It is currently in the process of absorbing smaller satellite galaxies, such as the Sagittarius dwarf galaxy. These interactions leave behind streams of stars that trace the orbits of the absorbed galaxies. In about 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy. This event, while seemingly catastrophic, will unfold over millions of years, reshaping both galaxies into a single, larger elliptical galaxy. At the heart of most galaxies lies a supermassive black hole, which plays a critical role in their evolution. These black holes can influence their host galaxies through powerful jets and winds that regulate star formation. Active galactic nuclei (GN), fueled by matter falling into the central black hole, can outshine entire galaxies, driving away gas and limiting future star formation. This process, known as feedback, is essential for understanding the balance between galaxy growth and quiescence. The availability of gas is a key factor in a galaxy's life cycle. Galaxies with abundant gas can sustain star formation for billions of years, while those that lose their gas through interactions or internal processes eventually become red and dead, dominated by old, inactive stars. The environments in which galaxies reside also play a role. Galaxies in dense clusters experience more frequent interactions and stripping of their gas, accelerating their evolution. Understanding the life cycle of galaxies is a window into the universe's past and future. Through observations with telescopes like Hubble and simulations of cosmic evolution, scientists are unraveling the intricate processes that shape galaxies over billions of years. These studies reveal the interconnectedness of the cosmos, where the fate of a single galaxy is tied to the larger structures of the universe. The life cycle of galaxies reminds us of the dynamic nature of the cosmos. Galaxies are not static entities but are constantly evolving, colliding, and transforming. Their stories are written in the stars, nebulae, and black holes that compose them, offering a glimpse into the grand processes that govern the universe. By studying galaxies, we learn not only about their individual histories, but also about the larger forces at work, shaping the cosmos on the grandest scales. The mystery of dark matter, the hidden backbone of the universe. Dark matter is one of the most profound mysteries in modern astrophysics, making up about 27% of the universe's total mass energy content. Unlike ordinary matter, which emits or absorbs light, dark matter interacts only through gravity, making it invisible to telescopes. Yet its influence is undeniable, shaping the structure and evolution of the cosmos on every scale. The story of dark matter begins with unexpected observations. In the 1930s, astronomer Fritz Zwicky studied the Coma Cluster, a massive grouping of galaxies, and noticed something strange. The galaxies were moving too quickly to be held together by the visible matter in the cluster. He concluded that there must be an unseen mass providing the necessary gravitational pull. Decades later, Vera Rubin's studies of galaxy rotation curves confirmed this phenomenon. She discovered that the outer regions of galaxies rotate as fast as their inner regions, defying the expectations based solely on visible matter. These observations provided strong evidence for an invisible substance, dark matter. Dark matter's gravitational pull is crucial for understanding the large-scale structure of the universe. After the Big Bang, tiny fluctuations in the density of matter were amplified by gravity, creating the cosmic web. Dark matter served as the scaffolding for this web, pulling ordinary matter into dense regions where galaxies and clusters formed. Without dark matter, the universe would look vastly different, with fewer galaxies and less structure. Scientists believe that dark matter is composed of particles, but their exact nature remains unknown. One leading candidate is WIMPs, weakly interacting massive particles, which are hypothesized to interact weakly with ordinary matter. Another possibility is exions, ultra-light particles that could form a cosmic field influencing galaxy formation. Some theories even propose that dark matter could be composed of galaxies, massive compact halo objects, such as black holes, neutron stars, or other compact objects that are difficult to detect. However, galaxies alone cannot account for the total amount of dark matter observed. Efforts to detect dark matter directly have been ongoing for decades. Experiments like SIN-1T and Lux Zeppelin aim to observe the rare interactions between dark matter particles and ordinary matter. These experiments involve ultra-sensitive detectors placed deep underground to shield them from cosmic rays and other background noise. So far, these searches have yielded no definitive results, but they have provided valuable constraints on the properties of dark matter particles. Indirect detection methods focus on observing the effects of dark matter annihilation or decay. If dark matter particles annihilate each other, they could produce gamma rays, neutrinos, or other particles that can be detected by observatories like Fermi Gamma Ray Space Telescope. Additionally, astrophysical phenomena such as gravitational lensing, where dark matter bends the path of light from distant galaxies, provide indirect evidence of its presence. These lensing effects have been used to map the distribution of dark matter in galaxy clusters, revealing structures invisible to traditional telescopes. Dark matter also plays a role in the formation and evolution of galaxies. Without the gravitational influence of dark matter halos, galaxies would not have formed as efficiently or retained their shapes over billions of years. The Milky Way, for example, is surrounded by a vast halo of dark matter that outweighs its visible components. This halo extends far beyond the galaxy's visible edge, influencing the motion of stars and satellite galaxies. While dark matter has become a cornerstone of cosmology, alternative theories have emerged to explain the phenomena it accounts for. Modified Newtonian dynamics, MOND, proposes that gravity behaves differently at very low accelerations, eliminating the need for dark matter. Other theories suggest that dark matter might interact with itself or have additional properties beyond its gravitational effects. These ideas remain speculative but highlight the ongoing effort to understand this enigmatic substance. The study of dark matter challenges our understanding of the universe at its most fundamental level. It forces us to confront the possibility that the majority of the cosmos is composed of something entirely unlike the matter we know. As experiments become more sensitive and observations more precise, we may be on the brink of uncovering the true nature of dark matter, solving one of the greatest puzzles in astrophysics. Dark matter reminds us that the universe is not only vast but also deeply mysterious. It is a silent force, invisible yet essential, shaping the cosmos from the earliest moments after the Big Bang to the formation of galaxies and clusters. By seeking to understand dark matter, we explore the hidden architecture of the universe, uncovering the unseen threads that bind the cosmos together. The power of supernovae, the universe's explosive architects. Supernovae are among the most powerful and transformative events in the universe, marking the dramatic deaths of massive stars. These colossal explosions release more energy in a few seconds than our Sun will emit over its entire 10 billion-year lifespan. Beyond their sheer power, supernovae play a critical role in shaping galaxies, seeding the cosmos with heavy elements, and driving the cycle of stellar evolution. The journey to a supernova begins in the heart of a massive star, one with at least 8 times the mass of the Sun. Throughout its life, the star burns hydrogen in its core through nuclear fusion, producing helium and releasing energy that counteracts the inward pull of gravity. As the star ages, it fuses progressively heavier elements, helium into carbon, carbon into oxygen, and so on, until it reaches iron. Fusion of iron does not produce energy. Instead, it absorbs it. Without the outward pressure of fusion to counterbalance gravity, the star's core collapses in a matter of seconds, triggering a catastrophic explosion. There are 2 main types of supernovae, core collapse and thermonuclear. Core collapse supernovae occur in massive stars, as described above, when the core implodes and rebounds, sending shockwaves through the outer layers. Thermonuclear supernovae, on the other hand, involve white dwarfs in binary systems. When a white dwarf accretes enough material from its companion star to exceed the Chandrasekhar limit, about 1.4 times the mass of the Sun, it undergoes a runaway fusion reaction, completely obliterating itself. The effects of a supernova are far-reaching and profound. The explosion generates shock waves that compress nearby gas and dust, triggering the formation of new stars. This process helps recycle material within galaxies, ensuring the continuous birth of stellar generations. Supernovae also release vast amounts of heavy elements, such as gold, silver, and uranium, which are scattered into space and incorporated into future stars, planets, and even life itself. Without supernovae, the universe would lack the diversity of elements needed for complex chemistry and biology. Supernovae are also essential for understanding cosmic distances. Type Ia supernovae, a subtype of thermonuclear explosions, have a consistent peak brightness, making them valuable standard candles for measuring distances across the universe. Observations of these supernovae in the late 1990s led to the discovery of dark energy, revealing that the universe's expansion is accelerating. One of the most famous remnants of a supernova is the Crab Nebula, located about 6,500 light-years away in the constellation Taurus. This nebula was formed by a supernova observed by Chinese astronomers in 1054 AD. At its center lies a pulsar, a rapidly rotating neutron star left behind by the explosion. Pulsars are some of the densest objects in the universe, with masses greater than the Sun compressed into a sphere only a few kilometers wide. Their intense magnetic fields and rapid rotation produce beams of radiation that sweep across the sky like cosmic lighthouses. Supernovae are also responsible for creating some of the most exotic objects in the universe, black holes. When a massive star's core collapses beyond the neutron star stage, it forms a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. These black holes often interact with their surroundings, accreting matter and emitting powerful jets that can influence the evolution of their host galaxies. Despite their destructive power, supernovae are not random. They are a natural part of the universe's life cycle. They occur roughly once every century in a galaxy like the Milky Way. Though many are obscured by interstellar dust and go unnoticed, advances in observational technology, such as wide-field surveys and neutrino detectors, are improving our ability to detect and study these events. Observing supernovae in other galaxies provides critical insights into the processes that shape galaxies and drive cosmic evolution. The study of supernovae extends beyond their physical effects. These explosions challenge our understanding of physics under extreme conditions. The intense heat and pressure during a supernova produce neutrinos, ghost-like particles that carry away a significant portion of the explosion's energy. Detecting these neutrinos allows scientists to probe the inner workings of the explosion, revealing details about the star's core collapse and nuclear reactions. Supernovae are more than cosmic explosions. They are architects of the universe. They drive the formation of stars, distribute the elements essential for life, and shape the structure of galaxies. Through their violent endings, stars give rise to new beginnings, ensuring the continuous evolution of the cosmos. By studying supernovae, we not only uncover the mechanisms of these spectacular events, but also deepen our understanding of the universe's interconnectedness and the cycles that define it. Black holes and the singularities within. Mysteries of infinite density. Black holes are some of the most enigmatic and extreme objects in the universe, where the very fabric of space and time is stretched to its limits. These regions of infinite density, known as singularities, form when massive amounts of matter collapse under their own gravity, creating a point where the laws of physics as we know them cease to function. Encased within an event horizon, a boundary beyond which nothing, not even light, can escape, black holes challenge our understanding of gravity, quantum mechanics, and the nature of reality itself. The formation of a black hole begins with the death of a massive star. When a star exhausts its nuclear fuel, it can no longer generate the pressure needed to counteract gravity. For stars at least 20 times the mass of the Sun, this collapse is unstoppable, compressing the core into a singularity and expelling the outer layers in a supernova explosion. What remains is a black hole, an object so dense that its escape velocity exceeds the speed of light. The size of the event horizon, known as the Schwarzschild radius, depends on the black hole's mass. For a black hole with the mass of the Sun, the radius would be just 3 kilometers. Black holes come in a variety of sizes, each with unique properties and behaviors. Stellar mass black holes, formed from collapsing stars, typically range from a few to tens of times the mass of the Sun. Supermassive black holes, on the other hand, have masses millions or billions of times greater and reside at the centers of most galaxies, including our Milky Way. The origin of these cosmic giants remains a mystery, with theories ranging from the direct collapse of massive gas clouds in the early universe to the merger of smaller black holes over billions of years. At the smallest end of the spectrum are hypothetical primordial black holes, which may have formed in the high-energy conditions of the early universe. These tiny black holes, if they exist, could provide insights into the nature of dark matter, as some theories suggest that primordial black holes could account for part of the unseen mass in the universe. Despite their fearsome reputation, black holes are not just cosmic destroyers. They play a crucial role in the evolution of galaxies and the cosmos at large. The immense gravitational pull of supermassive black holes influences the motion of stars and gas in their host galaxies, shaping their structure and dynamics. Active galactic nuclei, AGN, powered by matter falling into a supermassive black hole, emit enormous amounts of energy, outshining entire galaxies and driving powerful jets of particles that can stretch for thousands of light years. These jets regulate star formation by heating and expelling gas, preventing it from condensing into new stars. One of the most significant breakthroughs in black hole research came in 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the merger of two black holes. This observation not only confirmed the existence of black hole mergers, but also opened a new era of multi-messenger astronomy, where gravitational waves complement traditional observations to provide a more complete picture of cosmic phenomena. Since then, dozens of black hole mergers have been detected, revealing a population of black holes that had previously been hidden from view. The study of black holes also delves into the frontiers of theoretical physics. At the heart of a black hole lies the singularity, a point where gravity becomes infinite and space-time curves infinitely. This breakdown of general relativity suggests that a more fundamental theory, such as quantum gravity, is needed to describe the conditions within a singularity. Some theories propose that singularities may not exist as true points, but are instead regions where quantum effects dominate, potentially resolving the infinities predicted by classical physics. Black holes also challenge our understanding of information and thermodynamics. According to Stephen Hawking, black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This process causes black holes to lose mass and eventually evaporate over trillions of years. However, this raises the question of what happens to the information about the matter that fell into the black hole, a puzzle known as the black hole information paradox. Resolving this paradox could provide insights into the fundamental nature of space, time, and entropy. Observing black holes directly has always been a challenge, given their invisibility. However, in 2019, the Event Horizon Telescope, EAT, captured the first ever image of a black hole's shadow located in the center of the galaxy M87. This groundbreaking achievement revealed a glowing ring of hot gas encircling the event horizon, providing visual confirmation of these mysterious objects. Future observations aim to capture more detailed images, study the dynamics of accretion disks, and uncover the behavior of magnetic fields near black holes. Black holes are not just cosmic anomalies, they are gateways to understanding the universe's most extreme conditions. They test the boundaries of our knowledge, pushing us to reconcile general relativity with quantum mechanics and explore the limits of space and time. These enigmatic objects remind us that the cosmos is filled with phenomena that defy intuition, challenging us to think beyond our current understanding and inspiring us to continue exploring the unknown. The cosmic microwave background, echoes of the Big Bang. The cosmic microwave background, CMB, is one of the most profound and illuminating discoveries in modern cosmology. It is the faint afterglow of the Big Bang, a relic of the moment when the universe first became transparent, around 380,000 years after its inception. This ancient light, stretched into microwaves by billions of years of cosmic expansion, carries a wealth of information about the early universe, its composition, and its evolution. The journey of the CMB begins in the primordial plasma of the early universe. Shortly after the Big Bang, the cosmos was a searing hot soup of particles, including protons, neutrons, and electrons, constantly interacting with photons, particles of light. These interactions prevented photons from traveling freely, effectively making the universe opaque. As the universe expanded and cooled, temperatures dropped to around 3000 Kelvin, allowing electrons to combine with protons and form neutral hydrogen atoms. This event, known as recombination, marked the first time photons travel unimpeded, creating the CMB we observe today. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB was initially detected as a faint, uniform background noise in all directions. Its discovery confirmed key predictions of the Big Bang theory and provided strong evidence against the competing steady-state model of the universe. What makes the CMB so remarkable is its uniformity. Its temperature is nearly the same, around 2.7 Kelvin across the entire sky. However, tiny fluctuations, measured to just 1 part in 100,000, reveal subtle differences in density that seeded the formation of galaxies and large-scale cosmic structures. Mapping the CMB has become a cornerstone of cosmology. Observatories like COBE, Cosmic Background Explorer, MOP, Wilkinson Microwave Anisotropy Probe, and Planck have provided increasingly detailed mean temperature and polarization. These maps offer a snapshot of the universe when it was less than 400,000 years old, revealing its fundamental properties, such as its age, composition, and geometry. One of the most critical pieces of information derived from the CMB is the universe's composition. The relative proportions of ordinary matter, dark matter, and dark energy are encoded in the patterns of temperature fluctuations. These data indicate that the universe is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, confirming that the vast majority of the cosmos is made up of unseen and poorly understood components. The CMB also provides insights into the universe's geometry and rate of expansion. Observations have confirmed that the universe is flat, meaning that parallel lines remain parallel as they extend across cosmic distances. This flatness has profound implications for the amount of matter and energy in the universe and supports the theory of cosmic inflation, a rapid expansion that occurred in the first fraction of a second after the Big Bang. Inflation stretched any initial curvature, leaving the universe nearly flat on observable scales. The polarization of the CMB adds another layer of information. As light scattered off free electrons during recombination, it became slightly polarized. This polarization pattern contains clues about the influence of gravitational waves from the inflationary period, offering a potential window into the universe's earliest moments. Detecting these primordial gravitational waves would be a groundbreaking discovery, providing direct evidence of inflation and a deeper understanding of the universe's birth. Another intriguing feature of the CMB is the cold spot, an unusually large and low-temperature region in the CMB map. Its origin remains a mystery, with theories ranging from statistical anomalies to interactions with large-scale cosmic structures like supervoids. Some speculative ideas even suggest that the cold spot could hint at a collision between our universe and another in a multiverse scenario, though this remains purely hypothetical. Studying the CMB is not without its challenges. The faint signals of the CMB must be disentangled from foreground emissions, such as radiation from our galaxy and other astrophysical sources. Advanced data analysis techniques and instruments sensitive to specific frequencies have been developed to overcome these obstacles, ensuring the most accurate measurements possible. The CMB is not just a relic of the past, it is a tool for exploring the future of cosmology. By continuing to refine our measurements and theories, scientists hope to uncover deeper truths about the nature of dark matter, dark energy, and the fundamental forces that shape the universe. Upcoming missions, like the LIGHT-by-RD satellite, aim to measure the CMB's polarization with unprecedented precision, pushing the boundary we can learn from this ancient light. In many ways, the CMB is a cosmic Rosetta Stone, providing a link between the earliest moments of the universe and its current state. It tells a story of transformation, from a seething plasma to a structured cosmos filled with galaxies, stars, and planets. Through the study of the CMB, we glimpse the origins of everything we see today, connecting us to the very birth of space and time. The multiverse, beyond our observable universe. The concept of the multiverse, a collection of potentially infinite universes beyond our own, is one of the most intriguing and speculative ideas in modern science. While our observable universe is vast and seemingly all-encompassing, the multiverse suggests that it may be just one bubble among countless others. Each of these universes could have its own unique properties, physical laws, and even dimensions, challenging our understanding of existence and raising profound philosophical questions. The idea of the multiverse emerges from several branches of physics and cosmology. One of the most compelling arguments comes from inflationary theory, which describes a rapid expansion of space-time shortly after the Big Bang. According to this theory, inflation didn't stop everywhere at the same time. Instead, certain regions of space continued to inflate, creating bubbles of space-time. Each bubble could become its own universe, with its own distinct properties and constants. This process, known as eternal inflation, suggests that the creation of universes is an ongoing phenomenon, potentially giving rise to an infinite multiverse. Another perspective comes from string theory, a framework that seeks to unify all fundamental forces by describing particles as tiny, vibrating strings. String theory predicts the existence of extra dimensions beyond the familiar three of space and one of time, which could give rise to universes with different physical laws. These universes might exist in a higher dimensional space, separate from ours, but potentially connected through phenomena like wormholes or quantum entanglement. Quantum mechanics also hints at the possibility of a multiverse. The many worlds interpretation of quantum mechanics suggests that every quantum decision creates a branching of realities. In this view, every possible outcome of a quantum event occurs in a separate universe. For example, in one universe, a coin flip lands heads, while in another it lands tails. If true, this interpretation implies that there are as many universes as there are possible quantum outcomes, an unimaginably vast number. The multiverse concept also addresses certain puzzles in cosmology. One such puzzle is the fine-tuning of the physical constants that govern our universe. For instance, the strength of gravity, the charge of the electron, and the cosmological constant all have values that allow for the existence of stars, planets, and life. If these constants were even slightly different, the universe might be lifeless. The multiverse offers a potential explanation. If there are countless universes with varying constants, it's not surprising that at least one would have the right conditions for life ours. While the multiverse is a fascinating idea, it remains highly speculative and controversial. One of the main challenges is that other universes, if they exist, may be fundamentally unobservable. They could lie beyond our cosmic horizon, meaning their light hasn't had time to reach us, or they might exist in entirely separate dimensions or realms inaccessible to our instruments. This lack of direct evidence makes the multiverse difficult to test scientifically, leading some critics to argue that it belongs more to the realm of philosophy than empirical science. Despite these challenges, there are indirect ways to explore the multiverse. For instance, if the multiverse arises from inflation, certain signatures might be imprinted in the cosmic microwave background, CMB. Patterns of temperature fluctuations or anomalies, such as the cold spot, could hint at interactions between our universe and others. Similarly, the discovery of specific features in particle physics, like the properties of the Higgs boson or evidence for extra dimensions, could provide support for theories that predict a multiverse. The multiverse also raises profound philosophical and existential questions. If there are infinite universes, does that mean there are infinite versions of you, each living a slightly different life? Are there universes where the laws of physics prevent the existence of stars, or where time flows backward? These ideas challenge our understanding of identity, reality, and the nature of existence, suggesting that our universe might be just one chapter in an infinitely larger story. While we may never have direct evidence of the multiverse, its study pushes the boundaries of human knowledge and imagination. It forces us to grapple with the limits of observation, the nature of reality, and the vast possibilities that lie beyond our cosmic horizon. The multiverse, if real, would fundamentally alter our understanding of the cosmos, transforming our perception of the universe from a singular entity to an infinite expanse of possibilities. Whether or not the multiverse exists, the exploration of this concept reminds us of the power of human curiosity. It challenges us to think beyond the limits of what we can see and measure, daring us to imagine a reality far grander than we ever thought possible. The multiverse invites us to ponder the ultimate question. If our universe is not unique, what does that mean for our place within the grand tapestry of existence? Gravitational waves, listening to the universe's invisible symphony. Gravitational waves are one of the most groundbreaking discoveries in modern astrophysics, offering a new way to observe the universe. These ripples in the fabric of space-time, first predicted by Albert Einstein in 1916, as part of his general theory of relativity, are generated by some of the most energetic events in the cosmos. Unlike electromagnetic waves, which include visible light, gravitational waves carry information about their sources by distorting space itself, making them a unique and complementary tool for studying cosmic phenomena. The existence of gravitational waves remained theoretical for nearly a century until 2015. When the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection. The event, known as GU 15914, involved the collision and merger of two black holes, located 1.3 billion light-years away. This discovery confirmed Einstein's predictions and opened a new era in astronomy, allowing scientists to listen to the universe for the first time. Gravitational waves are produced by massive objects accelerating through space. Common sources include merging black holes, neutron-star collisions, and supernova explosions. As these events occur, they create ripples in space-time that propagate outward at the speed of light. These waves stretch and compress space as they pass. But the distortions they cause are incredibly small, smaller than the width of a proton. Detecting them requires highly sensitive instruments and advanced techniques. LIGO, along with its European counterpart Virgo, uses laser interferometry to measure these minute distortions. Each observatory consists of two perpendicular arms, each several kilometers long. A laser beam is split and sent down each arm, then reflected back by mirrors. Gravitational waves slightly alter the distance between the mirrors, creating an interference pattern in the recombined laser beam. By comparing data from multiple detectors, scientists can pinpoint the source of the waves and determine the properties of the event that created them. The detection of gravitational waves has revolutionized our understanding of the cosmos. Before their discovery, black holes were studied indirectly through their interactions with nearby matter. Gravitational waves provide direct evidence of black holes and their mergers, revealing their masses, spins, and distances. They also offer insights into neutron stars, the remnants of supernovae, which can merge to produce both gravitational waves and electromagnetic signals like gamma-ray bursts. Observing these events in multiple ways, known as multi-messenger astronomy, provides a more complete picture of the universe. One of the most exciting observations came in 2017 with GU 17817, the merger of two neutron stars. This event produced gravitational waves, a gamma-ray burst, and light across the electromagnetic spectrum, allowing scientists to study it in unprecedented detail. The detection confirmed that such mergers are a primary source of heavy elements like gold and platinum, which are ejected into space during the collision. It also provided a new way to measure the Hubble constant, the rate of the universe's expansion, by comparing the gravitational wave signal with the light emitted by the event. Gravitational waves are not limited to individual events, they also offer insights into the universe's large-scale structure and evolution. Scientists hope to detect a background hum of gravitational waves produced by countless mergers over cosmic history. This stochastic background could reveal the cumulative effects of these events, providing a broader perspective on the universe's dynamics. Future gravitational wave observatories promise even more discoveries. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect lower frequency waves from supermassive black hole mergers and other large-scale phenomena. Ground-based detectors like LIGO and Virgo will be upgraded to increase their sensitivity, while next-generation facilities like the Einstein telescope aim to push the boundaries of detection even further. These advancements will allow scientists to study events deeper in the universe and farther back in time, potentially uncovering signals from the early moments after the Big Bang. The implications of gravitational wave astronomy extend beyond astrophysics. These waves provide a way to test general relativity in extreme conditions, such as near the event horizons of black holes. They could also shed light on the nature of dark matter and other exotic phenomena, such as cosmic strings, hypothetical defects in space-time formed during the universe's infancy. Gravitational waves might even carry information about the universe's earliest moments, offering a direct probe of the inflationary period that followed the Big Bang. The study of gravitational waves represents a profound shift in how we observe the universe. For centuries, astronomy was limited to the study of light and other forms of electromagnetic radiation. Gravitational waves add an entirely new dimension, allowing us to explore phenomena that would otherwise remain hidden. They are a testament to the ingenuity of human science, turning a theoretical prediction into a practical tool for unlocking the universe's secrets. Gravitational waves remind us that the universe is filled with unseen forces and interactions, shaping its evolution in ways we are only beginning to understand. By listening to these ripples in space-time, we gain a deeper appreciation of the cosmos's dynamic nature, from the violent mergers of black holes to the subtle echoes of the Big Bang itself. This new form of observation opens the door to discoveries that may redefine our understanding of reality, challenging us to expand our perspective and embrace the vastness of the unknown. Exoplanets and the search for Earth's twins. Exoplanets, planets orbiting stars beyond our solar system, represent one of the most exciting frontiers in modern astronomy. Since the first confirmed discovery in 1992, thousands of exoplanets have been detected, revealing a staggering diversity of worlds. These planets range from hot Jupiters and icy giants to rocky Earth-like planets, each offering new insights into the processes that govern planetary formation and the potential for life beyond Earth. The search for exoplanets begins with methods designed to detect their subtle effects on their parent stars. The most successful technique to date is the transit method, which observes the dimming of a star's light as a planet passes in front of it. This method, employed by missions like Kepler and TESS, transiting exoplanet survey satellite, has identified thousands of exoplanets by measuring the periodic dips in brightness caused by planetary transits. These observations provide critical information about a planet's size, orbit, and distance from its star. Another widely used technique is the radial velocity method, which measures the tiny wobble of a star caused by the gravitational pull of an orbiting planet. This method, often used in conjunction with the transit method, provides data on a planet's mass and helps determine its density, which in turn indicates whether the planet is rocky, gaseous, or a mix of the two. Together, these techniques have revolutionized our understanding of planetary systems, showing that they are far more varied and dynamic than our own solar system. One of the most tantalizing goals in exoplanet research is the discovery of Earth-like planets in the habitable zones of their stars. The habitable zone, often called the Goldilocks zone, is the region around a star where temperatures allow for liquid water to exist on a planet's surface, a key ingredient for life as we know it. Among the most promising discoveries is Proxima Centauri b, an Earth-sized planet orbiting the closest star to our solar system, just 4.24 light-years away. Although Proxima b lies within its star's habitable zone, its proximity to a flare-prone red dwarf raises questions about its potential habitability. The diversity of exoplanets has also challenged traditional models of planetary formation. For instance, the discovery of hot Jupiter's gas giants orbiting extremely close to their stars defied expectations based on our solar system, where gas giants like Jupiter and Saturn reside far from the Sun. These findings suggest that planetary migration, where planets move closer to or farther from their stars after forming, is a common and complex process. Other intriguing categories of exoplanets include super-Earths and mini-Neptunes, which have no direct analogues in our solar system. Super-Earths are larger than Earth but smaller than Neptune, and they may have thick atmospheres or vast oceans, providing unique environments for potential life. Mini-Neptunes, on the other hand, are smaller versions of Neptune and may have hydrogen-rich atmospheres or icy surfaces. These discoveries highlight the immense variety of planetary systems and the adaptability of planets to form under a wide range of conditions. The study of exoplanet atmospheres is a rapidly advancing field thanks to the capabilities of modern telescopes. By analyzing the light that passes through or reflects off an exoplanet's atmosphere during a transit, scientists can identify the chemical composition of the atmosphere. Key molecules like water vapor, carbon dioxide, methane, and oxygen are of particular interest, as they could indicate conditions favorable for life or even the presence of biological activity. The James Webb Space Telescope, JWST, launched in 2021, has brought the study of exoplanets to a new level. Its ability to observe in the infrared spectrum allows it to probe the atmospheres of distant planets with unprecedented precision. JWST's instruments can detect biosignature's chemical markers that suggest the presence of life, such as oxygen combined with methane or ozone. These capabilities bring us closer than ever to answering one of humanity's most profound questions: are we alone in the universe? Exoplanet research has also spurred the development of ambitious future missions. The European Space Agency's Ariel mission aims to survey the atmospheres of hundreds of exoplanets, while NASA's Habitable Worlds Observatory plans to search for Earth-like planets around Sun-like stars. These missions, combined with advances in technology and data analysis, promise to uncover new details about planetary systems and the potential for life beyond our solar system. The implications of exoplanet discoveries extend far beyond astronomy. They challenge our understanding of what makes a planet habitable, forcing us to consider the possibility of life in environments vastly different from those on Earth. They also highlight the adaptability of planetary systems, showing that planets can form and evolve in ways that were once thought impossible. This growing knowledge not only deepens our appreciation for the diversity of the cosmos, but also sharpens our focus in the search for life elsewhere. The quest to find Earth-like planets and potential signs of life is a journey of discovery that bridges science, philosophy, and human curiosity. Each new exoplanet adds to our understanding of the universe, showing us that our solar system is just one of countless possibilities. As we continue to explore these distant worlds, we come closer to understanding our place in the cosmos and the extraordinary potential for life to thrive in the vastness of space. Dark energy, the force accelerating the universe's expansion. Dark energy is one of the most profound and mysterious forces in the universe, driving the accelerated expansion of space and accounting for approximately 68% of the universe's total energy density. Its discovery in the late 1990s fundamentally altered our understanding of cosmology, revealing that the universe is not only expanding but doing so at an ever-increasing rate. Despite its immense influence, the true nature of dark energy remains one of the greatest unsolved mysteries in science. The story of dark energy begins with the observation of distant Type Ia supernovae explosions of white dwarf stars that serve as standard candles for measuring cosmic distances. In the 1990s, two independent research teams used these supernovae to map the universe's expansion history. To their astonishment, they found that the expansion of the universe was not slowing down, as previously assumed, but accelerating. This unexpected discovery suggested the presence of a repulsive force, later termed dark energy, counteracting the pull of gravity on cosmic scales. Dark energy's effects are most evident in the behavior of galaxies over vast distances. As space expands, galaxies are carried apart like raisins in a rising loaf of bread. However, the acceleration caused by dark energy means that galaxies farther away are receding from us faster than those nearby. This phenomenon, first observed by Edwin Hubble in the early 20th century, now carries a deeper significance, as it highlights the dynamic and ever-changing nature of the cosmos. The leading explanation for dark energy is the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Einstein initially included the cosmological constant to allow for a static universe, unaware at the time that the universe was expanding. After Hubble's discovery of cosmic expansion, Einstein famously referred to the constant as his greatest blunder. However, with the discovery of dark energy, the cosmological constant has gained new relevance, representing a form of energy inherent to the fabric of space itself. In this interpretation, dark energy is a constant energy density that fills space uniformly. As the universe expands, new space is created, and with it, more dark energy causing the expansion to accelerate. This model, known as the lambda-cold dark matter (LAC model, is the current standard in cosmology, successfully explaining many observed phenomena, including the large-scale structure of the universe and the anisotropies in the cosmic microwave background (CMB). Alternative theories propose that dark energy might not be constant but dynamic, evolving over time. These models, often referred to as quintessence, suggest that dark energy is a field that changes in strength as the universe expands. Unlike the cosmological constant, quintessence allows for variations in the rate of cosmic acceleration, potentially offering explanations for subtle discrepancies in observational data. However, such models require additional parameters and have yet to gain the same level of empirical support as the cosmological constant. Dark energy's influence extends far beyond the present. It plays a crucial role in determining the ultimate fate of the universe. If dark energy remains constant, the universe will continue to expand indefinitely, leading to a big freeze. In this scenario, galaxies will drift farther apart, stars will exhaust their nuclear fuel, and the cosmos will grow increasingly cold and dark over trillions of years. Alternatively, if dark energy's strength increases, it could lead to a big rip, where the expansion becomes so rapid that galaxies, stars, planets, and even atoms are torn apart. Conversely, if dark energy diminishes or reverses, the universe could collapse in a big crunch, returning to a hot, dense state similar to the conditions of the Big Bang. This cyclical model, while less favored by current observations, offers intriguing possibilities for a universe that perpetually renews itself. Observing dark energy directly is challenging, as it does not emit, absorb, or reflect light. Instead, its presence is inferred through its effects on the universe's expansion and the distribution of galaxies. Large-scale surveys, such as the Dark Energy Survey (DS) and the Euclid mission, aim to map the three-dimensional structure of the universe with unprecedented precision, providing new insights into dark energy's properties. These surveys measure phenomena such as baryon acoustic oscillations, ripples in the density of matter from the early universe, and weak gravitational lensing, the bending of light by mass, to refine our understanding of cosmic acceleration. One of the most intriguing aspects of dark energy is its connection to fundamental physics. Some theories suggest that dark energy could be linked to quantum fluctuations of the vacuum, where particles and antiparticles spontaneously appear and annihilate. Others propose that it might signal the breakdown of general relativity on large scales, pointing to the need for a more comprehensive theory of gravity. These possibilities highlight the profound implications of dark energy for our understanding of the universe's fundamental forces and components. The study of dark energy exemplifies the intersection of observation, theory, and imagination in science. It challenges us to confront the limits of our knowledge and to seek explanations for phenomena that lie beyond the reach of current models. By exploring the nature of dark energy, we not only deepen our understanding of the cosmos, but also illuminate the profound mysteries that define existence itself. Dark energy is a reminder that the universe is not static but dynamic and evolving. It forces us to question long-held assumptions about the nature of space, time, and matter, pushing the boundaries of human knowledge. As we continue to probe its secrets, dark energy promises to transform our understanding of the universe, offering a glimpse into the forces that shape its past, present, and future. The cosmic web, the universe's hidden skeleton. The cosmic web is the vast, interconnected structure of the universe, a network of filaments composed of dark matter, gas, and galaxies that stretches across hundreds of millions of light years. This intricate framework underpins the distribution of matter in the cosmos, connecting galaxy clusters and leaving vast empty regions known as voids. The cosmic web is not just a visual marvel, it is a fundamental component of the universe, revealing the influence of gravity and dark matter on cosmic evolution. The origins of the cosmic web trace back to the earliest moments after the Big Bang. During the universe's infancy, small quantum fluctuations in density were amplified by gravity, creating regions of higher and lower density. These fluctuations were imprinted in the cosmic microwave background, CMB, and served as the seeds for the formation of large-scale cosmic structures. Over billions of years, gravity pulled matter into dense regions, forming the filaments and nodes that define the cosmic web. The filaments of the cosmic web act as highways for matter, channeling gas and dark matter into galaxy clusters at the intersections of filaments. These dense regions, or nodes, are the sites of intense star formation and galaxy evolution. Between the filaments lie cosmic voids, vast, empty expanses where galaxies are few and far between. These voids can span tens to hundreds of millions of light years, creating a stark contrast to the densely packed filaments and clusters. Mapping the cosmic web has been a monumental achievement in modern astronomy. Large-scale surveys like the Sloan Digital Sky Survey (SES) have cataloged millions of galaxies, revealing the three-dimensional structure of the universe. These maps show how galaxies cluster along filaments, creating a spiderweb-like pattern that stretches across space. The distribution of galaxies in these surveys matches the predictions of cosmological simulations, confirming the role of dark matter in shaping the cosmic web. Dark matter is the invisible backbone of the cosmic web. While it does not emit or absorb light, its gravitational pull shapes the distribution of ordinary matter, guiding the formation of galaxies and clusters. Simulations of the universe's evolution, such as the Millennium Simulation and Illustris project, show how dark matter halos form around dense regions, attracting gas and forming the foundations for galaxies. Without dark matter, the cosmic web as we know it would not exist. The cosmic web is also a dynamic structure, evolving over billions of years. As the universe expands, filaments stretch and grow, while voids become emptier. Interactions between galaxies and clusters within the web drive cosmic evolution, triggering starbursts, supernovae, and the growth of supermassive black holes. These processes enrich the surrounding gas with heavy elements, spreading the building blocks of stars, planets, and life throughout the universe. Studying the cosmic web provides insights into the role of dark energy in shaping the universe. The accelerated expansion of space, driven by dark energy, affects the growth of cosmic structures, slowing the rate at which filaments and clusters form. By measuring the distribution and motion of galaxies within the web, astronomers can refine our understanding of dark energy's properties and its influence on the cosmos. One of the most exciting aspects of the cosmic web is its potential to reveal the origins of the universe. The patterns of density fluctuations in the web carry information about the conditions of the early universe, including the effects of inflation, a rapid expansion that occurred in the first fraction of a second after the Big Bang. By analyzing the distribution of matter in the cosmic web, scientists can test theories of inflation and probe the fundamental physics that govern the universe's birth. The cosmic web also serves as a laboratory for studying the interplay between galaxies, gas, and dark matter. Observations of gas flowing along filaments into clusters, known as the circumgalactic medium, provide clues about the processes that fuel star formation and black hole growth. These flows of matter are critical for understanding how galaxies evolve over time and how they maintain the balance between creation and destruction. Void regions within the cosmic web are equally fascinating. These vast, empty spaces provide a unique environment for studying the universe's expansion and testing theories of gravity. Because voids are dominated by dark energy rather than matter, they offer a clean laboratory for observing the effects of cosmic acceleration. Researchers have even proposed using voids to test alternative theories of gravity, such as modifications to general relativity. The study of the cosmic web is an ongoing effort, combining observations, simulations, and theoretical models to uncover the underlying structure of the universe. Future surveys, such as those conducted by the Vera C. Rubin Observatory and the Euclid mission, will provide even more detailed maps of the web, capturing its evolution over time and refining our understanding of dark matter and dark energy. The cosmic web is a testament to the interconnectedness of the universe. It shows how the smallest fluctuations in the early cosmos grew into the vast structures we see today, linking galaxies, clusters, and filaments in a grand cosmic tapestry. By exploring the web, we gain a deeper appreciation for the forces that shape the universe and our place within its intricate design. The evolution of stars, from formation to their spectacular endings. Stars are the engines of the universe, forging elements, radiating energy, and shaping the environments around them. Their life cycles span millions to billions of years, defined by a delicate balance between gravity and the energy released through nuclear fusion. Understanding the evolution of stars not only reveals the processes that govern their lifetimes, but also provides insight into the origins of the elements that make up everything we see, including life itself. Stars begin their lives in vast molecular clouds, regions of cold gas and dust scattered throughout galaxies. These clouds, often stretching across light years, are the nurseries of stellar birth. Within them, regions of higher density collapse under their own gravity, forming protostars. During this phase, gravitational energy is converted into heat, and the protostar begins to shine faintly. Eventually, when the core temperature reaches approximately 10 million Kelvin, hydrogen fusion ignites, marking the birth of a true star. The main sequence phase of a star's life is its most stable and longest-lasting period. During this time, the star fuses hydrogen into helium in its core, generating energy that counteracts the inward pull of gravity. The star's mass determines its position on the Hertzsprung-Russell (HR) diagram and its overall lifespan. Low-mass stars, like red dwarfs, burn their hydrogen slowly, living for tens to hundreds of billions of years, far longer than the current age of the universe. Medium-mass stars, such as the Sun, spend around 10 billion years on the main sequence before transitioning to later stages. High-mass stars, on the other hand, burn through their fuel rapidly, living for only a few million years. As a star exhausts its hydrogen fuel, its fate diverges based on its mass. Low and medium mass stars expand into red giants as their cores contract and their outer layers swell. In these stars, helium fusion begins, creating heavier elements like carbon and oxygen. Once the star runs out of helium, its outer layers are ejected, forming a planetary nebula, while the core becomes a white dwarf. These remnants, composed mostly of carbon and oxygen, gradually cool and fade over billions of years. High-mass stars undergo a far more dramatic transformation. After leaving the main sequence, they enter a series of fusion stages, creating progressively heavier elements in their cores. This process continues until iron is formed, the most stable element in terms of nuclear binding energy. Iron cannot undergo fusion to produce energy, so the core collapses under gravity, triggering a supernova explosion. These explosions release enormous amounts of energy, briefly outshining entire galaxies and scattering heavy elements into space. Supernovae are not just endings but also beginnings. The elements created in the cores of massive stars and during the explosion itself, such as gold, silver, and uranium, are expelled into the interstellar medium, enriching future generations of stars and planets. Without supernovae, the universe would lack the diversity of elements needed for complex chemistry and life. These explosions also trigger the formation of new stars by compressing nearby gas clouds, continuing the cycle of letter evolution. The remnants of supernovae depend on the star's mass. Stars with core masses between about 1.4 and 3 times the Sun's mass form neutron stars, ultra-dense, composed almost entirely of trons. These remnants are often found spinning rapidly and emitting beams of radiation, becoming pulsars. For the most massive stars, the core collapses into a black hole, a region where gravity is so intense that nothing, not even light, can escape. The evolution of binary stars introduces additional complexity. In these systems, mass transfer between stars can lead to phenomena such as type Iowa supernovae, which occur when a white dwarf accretes enough material from its companion to trigger a runaway fusion reaction. These explosions serve as standard candles for measuring cosmic distances, playing a critical role in our understanding of the universe's expansion. Stars also shape their environments through stellar wind streams of charged particles that carry away mass and energy. Massive stars, in particular, produce powerful winds that sculpt the surrounding gas, creating stunning nebulae and influencing the formation of nearby stars. These winds, combined with radiation pressure, help regulate star formation rates within galaxies. The study of stars extends beyond their life cycles to their broader impact on the cosmos. Stars are the primary sources of light and heat in the universe, driving the chemistry of planets and providing the conditions necessary for life. Their death seed galaxies with the elements needed for new stars and planetary systems, ensuring the continuity of cosmic evolution. Through observations with telescopes like Hubble and James Webb, as well as simulations of stellar dynamics, scientists continue to uncover the intricacies of stellar evolution. Each phase of a star's life offers a glimpse into the physical processes that govern the universe, from the fusion reactions in stellar cores to the explosive forces of supernovae. By studying stars, we not only learn about their lifetimes but also gain insight into the interconnected cycles that shape galaxies, influence cosmic structures, and create the conditions for life. Stars remind us that the universe is a place of both creation and destruction, where the death of one star can give rise to the birth of another. Their life cycles are a testament to the dynamic and ever-changing nature of the cosmos, a process that has been unfolding for billions of years and will continue for billions more. Through the light of the stars, we see the story of the universe itself, written across time and space. The James Webb Space Telescope, a new era of cosmic exploration. The James Webb Space Telescope, JWST, often called the successor to the Hubble Space Telescope, represents a transformative leap in humanity's ability to observe and understand the universe. Launched in December 2021, after decades of meticulous planning and engineering, JWST is the most powerful and complex space observatory ever built. Its mission is to peer into the deepest corners of the cosmos, unveiling the secrets of the universe's earliest moments, the birth and evolution of galaxies, and the atmospheric compositions of distant exoplanets. One of JWST's most groundbreaking features is its ability to observe in the infrared spectrum, a capability that sets it apart from its predecessor, Hubble, which primarily observes invisible and ultraviolet light. Infrared light has longer wavelengths than visible light, allowing it to pass through dust clouds that obscure many cosmic phenomena. This ability enables JWST to study regions like stellar nurseries, dense molecular clouds where stars and planets form with unparalleled clarity. The telescope's infrared vision also makes it uniquely suited to study the early universe. Due to the expansion of space, light from the first galaxies formed after the Big Bang has been stretched, or redshifted, into the infrared part of the spectrum. JWST can detect this ancient light, providing a window into a time when the universe was just a few 100 million years old. By studying these early galaxies, JWST aims to answer fundamental questions about how the first structures formed, how they evolved, and how they contributed to the reionization of the universe, a pivotal era when light began to travel freely through space. JWST's ability to observe faint, distant objects is due to its massive primary mirror, which measures 6.5 meters in diameter, more than twice the size of Hubble's mirror. Composed of 18 hexagonal segments coated in a thin layer of gold for optimal infrared reflectivity, the mirror collects and focuses light with extraordinary precision. To keep the telescope cool and ensure the purity of its infrared observations, JWST is equipped with a multi-layered sun shield the size of a tennis court. This shield blocks heat from the sun, earth, and moon, maintaining the telescope at an operating temperature of about -233 degrees Celsius, -388 degrees Fahrenheit. One of JWST's most exciting areas of research is the study of exoplanets and their atmospheres. By observing the light from a host star as it filters through an exoplanet's atmosphere during a transit, JWST can analyze the atmospheric composition of these distant worlds. This technique, known as transmission spectroscopy, allows scientists to identify key molecules such as water vapor, carbon dioxide, methane, and oxygen, potential indicators of habitability or even life. The telescope's early observations have already yielded groundbreaking results. JWST detected carbon dioxide in the atmosphere of an exoplanet for the first time and has begun characterizing the atmosphere of rocky planets' inhabitable zones. These studies are paving the way for the search for biosignatures, chemical markers that suggest the presence of life. While JWST cannot directly image Earth like planets in the habitable zones of sun-like stars, its findings will design of future missions aimed at detecting signs of life on other worlds. In addition to its studies of the early universe and exoplanets, JWST is providing new insights into the life cycles of stars. It has captured stunning images of stellar nurseries, such as the Carina Nebula, where young stars are carving out intricate shapes in surrounding clouds of gas and dust. JWST is also probing the final stages of stellar evolution, observing the complex structures of planetary nebulae and the environments around remnant supernova remnants. The telescope's capabilities extend to the study of galaxies across cosmic time. By observing galaxies at different stages of their evolution, JWST is unraveling the processes that drive their growth and transformation. It is shedding light on how supermassive black holes influence their host galaxies, how galaxies merge and interact, and how star formation rates have changed over billions of years. These observations are providing a more complete picture of the universe's history and the mechanisms that shape its large-scale structure. JWST is also contributing to our understanding of our own solar system. Its infrared observations are revealing new details about the atmospheres of gas giants like Jupiter and Saturn, the icy surfaces of moons such as Europa and Enceladus, and the composition of comets and asteroids. These studies are helping scientists piece together the history of the solar system and assess its potential for supporting life beyond Earth. The telescope's journey to success has not been without challenges. Delayed numerous times due to technical and budgetary issues, JWST's eventual launch and deployment required an unprecedented level of precision and coordination. Its intricate unfolding process, likened to an origami masterpiece, was a high-stakes operation involving the deployment of its sun shield, mirror segments, and instruments over the course of several weeks. The flawless execution of this process was a testament to the ingenuity and perseverance of the international team of scientists, engineers, and technicians behind the mission. JWST is a collaborative effort involving NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. This partnership has brought together expertise and resources from around the world, reflecting the shared goal of advancing humanity's understanding of the cosmos. The telescope's discoveries are freely shared with the global scientific community, fostering collaboration and inspiring a new generation of researchers. The James Webb Space Telescope is more than an instrument. It is a symbol of human curiosity and our relentless drive to explore the unknown. Its observations are rewriting textbooks, expanding our understanding of the universe, and inspiring us to ask new questions about our place in the cosmos. As it continues to operate over the coming decades, JWST will undoubtedly phenomena we cannot yet imagine, reminding us of the boundless possibilities of science and exploration. The birth of the solar system, from dust to planets. The formation of our solar system is a story that stretches back over 4.5 billion years, rooted in the dynamic process of a vast molecular cloud in our galaxy. This cosmic event gave rise to the Sun, the planets, moons, asteroids, and comets that form the intricate system we inhabit today. Understanding how the solar system came to be offers not only a glimpse into our own origins, but also insights into the processes shaping planetary systems across the cosmos. The story begins in a molecular cloud, a cold, dense region of gas and dust where stars are born. Within this cloud, a disturbance, possibly triggered by a nearby supernova explosion or the gravitational pull of a passing star, caused a region to collapse under its own gravity. As the cloud fragmented, one such region formed a dense core, which would become the solar nebula. This disk-shaped structure of gas and dust rotated rapidly as it contracted, with most of the material pulled toward the center, forming the protozoan. The proton grew hotter and denser as gravitational energy was converted into heat, igniting nuclear fusion when the temperature reached around 10 million Kelvin. This marked the birth of the Sun, the center of the nascent solar system. Surrounding the Sun, the remaining gas and dust in the solar nebula provided the raw material for planet formation. The process of planetary formation began with the aggregation of tiny particles in the disk. These particles collided and stuck together through electrostatic forces, forming larger clumps called planetesimals. Over time, these planetesimals grew into protoplanets through continued collisions and gravitational attraction. The inner regions of the disk, where temperatures were higher, gave rise to rocky planets like Earth and Mars, as volatile compounds like water and methane were driven away by the Sun's heat. In contrast, the cooler outer regions allowed gas giants like Jupiter and Saturn to form, accumulating thick atmospheres of hydrogen and helium. The formation of the gas giants played a critical role in shaping the solar system. Their immense gravitational influence sculpted the orbits of smaller bodies and cleared the surrounding space of debris. Jupiter, in particular, acted as a cosmic shield, deflecting many comets and asteroids that might otherwise have collided with the inner planets. However, it also destabilized some orbits, sending objects into the inner solar system, where they contributed to the heavy bombardment period, a time of intense asteroid and comet impacts that left lasting scars on planetary surfaces. The final stages of solar system formation were marked by a period of dynamic interactions and migrations. The young planets jockeyed for position, their orbits influenced by gravitational interactions with each other and the remnants of the solar nebula. This era, known as the Nice model after the city in France where it was developed, explains many features of the current solar system, such as the distribution of asteroids and the peculiar orbits of distant objects like Pluto. The Moon, Earth's closest companion, also owes its existence to the chaotic early solar system. The leading theory suggests that a Mars-sized body, named Theia, collided with the proto-Earth around 4.5 billion years ago. The impact ejected vast amounts of material into orbit, which coalesced to form the Moon. This event not only gave Earth a natural satellite, but also helped stabilize its axial tilt, contributing to the development of stable seasons and a hospitable climate. As the solar system matured, leftover debris formed the asteroid belt, Kuiper belt, and Oort cloud. The asteroid belt, located between Mars and Jupiter, consists of rocky remnants that never coalesced into a planet, likely due to Jupiter's gravitational interference. The Kuiper belt, beyond Neptune, is home to icy bodies like Pluto and Haumea, while the Oort cloud, a theoretical shell of icy objects, represents the distant frontier of the solar system, stretching nearly a light year from the Sun. Water, a critical ingredient for life on Earth, likely arrived during the late heavy bombardment period, delivered by icy comets and asteroids. These impacts enriched the young Earth with the volatile compounds necessary for its oceans and atmosphere, setting the stage for the emergence of life. Recent studies also suggest that Earth's interior may have contained significant water from its formation, indicating a complex interplay of sources. The study of solar system formation continues to evolve, driven by observations of exoplanetary systems and advances in simulation technology. Comparing our solar system to others has revealed both striking similarities and intriguing differences. Many exoplanet systems host super-Earths and hot Jupiters, types of planets that are absent in our solar system. These findings challenge existing models and suggest that our system may be an outlier in some respects. Missions like NASA's OSIRIS-REx, which recently returned samples from the asteroid Bennu, and ESA's Rosetta, which studied the comet 67P Churyumov-Gerasimenko, are providing direct insights to the building blocks of the solar system. These pristine materials offer a window into the conditions and processes that prevailed during the system's formation, helping scientists refine their models and answer long-standing questions.
The formation of the solar system is a tale of chaos and creativity, a process of destruction and renewal that transformed a cloud of gas and dust into a complex and dynamic system. Each planet, moon, and asteroid carries the imprint of this history, offering clues about the forces that shaped it. By studying these objects, we not only learn about our own origins, but also gain a deeper understanding of the universal processes that govern planetary systems across the cosmos.
The birth and death of the universe, cycles of creation and destruction. The universe, vast and seemingly eternal, has a finite history that began approximately 13.8 billion years ago with the Big Bang. Its story is one of constant evolution, marked by cycles of creation and destruction that continue to shape its structure and dynamics. While much has been uncovered about its origins and growth, the ultimate fate of the cosmos remains one of the most profound mysteries in science. The beginning, the Big Bang and cosmic inflation. The universe began as an incomprehensibly hot and dense point of singularity. In the first fractions of a second after the Big Bang, the universe underwent an era of rapid expansion known as cosmic inflation. During this phase, the universe expanded exponentially, smoothing out irregularities and laying the groundwork for the large-scale structure observed today. Inflation stretched quantum fluctuations to macroscopic scales, seeding the tiny variations in density that would later grow into galaxies, clusters, and the cosmic web. As inflation ended, the universe transitioned into the hot Big Bang phase, filled with a dense plasma of particles. During the first few minutes, a process called primordial nucleosynthesis produced the light elements hydrogen, helium, and trace amounts of lithium. For the next 380,000 years, the universe was opaque, as photons continuously interacted with free electrons in the plasma. This era ended with recombination, when electrons bonded with nuclei to form neutral atoms, allowing light to travel freely. The resulting radiation, now observed as the cosmic microwave background, CMB, provides a snapshot of the universe at this pivotal moment. The growth. structure formation, and the role of dark matter. After recombination, the universe entered the Dark Ages, a period before the formation of the first stars. During this time, gravity amplified the density fluctuations seeded during inflation, drawing matter into the first clumps. These clumps, composed primarily of dark matter, served as scaffolds for the formation of galaxies. Hydrogen and helium gas accumulated in these regions, eventually collapsing to form the first stars and galaxies. The first stars, known as population III stars, were massive and short-lived, ending their lives in powerful supernovae that enriched the surrounding gas with heavier elements. This enrichment enabled the formation of more complex structures, including the first planetary systems. Over billions of years, galaxies grew through mergers and accretion, forming the vast cosmic web of filaments and clusters observed today. Dark matter played a critical role in this process. Its gravitational influence dictated the distribution of ordinary matter, shaping the large-scale structure of the universe. Without dark matter, the universe would lack the intricate web of galaxies and clusters that define its structure. The accelerating universe, the role of dark energy. In the 20th century, astronomers discovered that the universe is expanding, a finding attributed to the work of Edwin Hubble. Initially, it was believed that this expansion was slowing due to the pull of gravity. However, observations of distant Type Iowa supernovae in the late 1990s revealed that the expansion is accelerating, driven by a mysterious force known as dark energy. This discovery fundamentally changed our understanding of the universe, indicating that dark energy dominates its energy budget, accounting for about 68% of its total content. Dark energy's influence grows as the universe expands, pulling galaxies apart and preventing the formation of new structures. Over time, it is expected to lead to a state of isolation, where galaxies drift so far apart that they become invisible to each other. This scenario, often referred to as the Big Freeze, suggests a cold and dark future for the universe. The end. Theories of cosmic fate. The ultimate fate of the universe depends on the interplay between dark energy, dark matter, and gravity. Several scenarios have been proposed.
The Big Freeze. If dark energy remains constant, the universe will continue expanding indefinitely. Over trillions of years, star formation will cease as galaxies exhaust their gas reserves. Existing stars will burn out, leaving only black holes, white dwarfs, and neutron stars. Even these remnants will eventually decay through processes like Hawking radiation, leaving a cold and empty cosmos.
The Big Rip. In some models, dark energy's strength increases over time. If this occurs, it could tear apart galaxies, stars, planets, and even a catastrophic event known as the Big Rip. This scenario represents the ultimate triumph of dark energy over all other forces. The Big Crunch and Big Bounce. If dark energy reverses or weakens, the universe could stop expanding and begin contracting. This contraction could culminate in a big crunch, where the universe collapses back into a hot, dense state. Some theories suggest that this collapse might trigger a new Big Bang, initiating a cyclical model of expansion and contraction, a Big Bounce. Vacuum decay. The universe may exist in a metastable state with a false vacuum energy level. A quantum fluctuation could cause it to transition to a lower energy true vacuum, resulting in a bubble of destruction that propagates at the speed of light, altering the universe's fundamental laws. Probing the universe's fate. Astronomers and physicists are actively investigating these scenarios by studying the properties of dark energy, the distribution of dark matter, and the universe's large-scale structure. Observatories like the Dark Energy Survey, DES, the Euclid mission, and the Vera C. Rubin Observatory are mapping the cosmos in unprecedented detail, measuring the effects of dark energy on galaxy clustering and the expansion rate. Gravitational wave observatories, such as LIGO and Virgo, are also contributing by detecting signals from merging black holes and neutron stars, which offer insights into the universe's evolution. Meanwhile, particle physics experiments aim to uncover the nature of dark matter and its interactions with ordinary matter, which could have profound implications for understanding the universe's ultimate fate. The cycle of creation and destruction. While the end of the universe remains uncertain, its story is one of continuous cycles. Stars form from the remnants of previous generations, galaxies grow through mergers, and elements forged in stellar cores are recycled into new stars and planets. Even in the distant future, when the cosmos may seem barren, the processes that defined its early history, gravity, thermodynamics, and quantum mechanics, will continue to shape its evolution. The birth and death of the universe remind us of the dynamic nature of the cosmos. It is a place of constant change, where destruction often paves the way for creation. By studying the universe's history and contemplating its future, we gain not only scientific insights, but also a deeper appreciation for the intricate interconnected forces that define existence itself. The role of black holes in galactic evolution. Black holes, once considered enigmatic anomalies of the universe, are now recognized as critical players in the evolution of galaxies. These cosmic giants, ranging from stellar mass black holes to supermassive behemoths millions or billions of times the sun's mass, influence their surroundings in profound ways. Their gravitational pull, energy output, and interactions with nearby matter shape the structure and behavior of galaxies, making them central to the cosmic story.
Supermassive black holes, the anchors of galaxies.
At the heart of nearly every large galaxy lies a supermassive black hole. The Milky Way, for instance, harbors Sagittarius A, a black hole with a mass of about 4 million suns. These central black holes act as gravitational anchors, influencing the motions of stars and gas within their host galaxies. Observations of stars orbiting Sagittarius A, for example, have provided direct evidence of its presence, with their rapid, elliptical motions pointing to an incredibly dense, invisible object. While the exact origins of supermassive black holes remain a mystery, they are thought to have formed from the collapse of massive gas clouds in the early universe, or from the growth of smaller black holes through mergers and accretion. Regardless of their beginnings, these black holes have grown over billions of years, consuming surrounding matter and merging with other black holes during galaxy collisions. Active galactic nuclei and quasars. When a supermassive black hole actively accretes matter, it can transform into an active galactic nucleus, AGN, emitting vast amounts of energy. As gas and dust spiral into the black hole, they form an accretion disk that becomes heated to millions of degrees, radiating in X-rays, ultraviolet, and visible light. AGNs can outshine their host galaxies, making them some of the brightest objects in the universe. Quasars, the most luminous type of AGN, are powered by supermassive black holes consuming matter at astonishing rates. Observed in the distant universe, quasars provide a glimpse into the early stages of galaxy evolution, when black holes and their host galaxies were still forming. The energy output of quasars can have dramatic effects on their surroundings, driving away gas and halting star formation in a process known as quenching. This feedback mechanism plays a key role in regulating the growth of galaxies. Feedback mechanisms shaping galaxies. Black holes exert influence far beyond their immediate surroundings through feedback processes. As matter falls into a black hole, it releases energy that can heat or expel gas in the host galaxy. This feedback comes in two primary forms, radiative and kinetic. Radiative feedback involves the intense radiation from the accretion disk, which heats the surrounding gas and prevents it from cooling and condensing into stars. Kinetic feedback, on the other hand, is driven by powerful jets of particles launched from the poles of the accretion disk at near light speeds. These jets can extend thousands of light years, carving out cavities in galaxy clusters and redistributing matter across vast distances. These feedback processes are crucial for understanding the co-evolution of galaxies and their central black holes. Observations show a correlation between the mass of a galaxy's central black hole and the properties of its bulge, such as its mass and velocity dispersion. This relationship, known as the M-sigma relation, suggests a close connection between black hole growth and galaxy evolution, likely mediated by feedback. Black holes and galaxy mergers. Galaxy mergers are among the most dramatic events in the universe, and black holes play a central role in these cosmic collisions. When two galaxies merge, their central black holes are drawn together, forming a binary system. Over time, these black holes spiral inward, emitting gravitational waves as they lose energy. The final stages of this process, when the black holes merge, produce powerful gravitational wave signals that can be detected by observatories like LIGO and Virgo. The merger of galaxies and their black holes triggers bursts of star formation, as gas clouds collide and compress. However, the energy released by the merging black holes can also expel gas, quenching star formation and leaving behind a more passive galaxy. These interactions help explain the transition of galaxies from blue, star-forming systems to red, quiescent ones. Primordial black holes in early galaxy formation. In addition to supermassive black holes, the early universe may have hosted primordial black holes, hypothetical remnants from the Big Bang. These objects, if they exist, could have served as seeds for the formation of supermassive black holes, providing a head start in their growth. They may also contribute to the mysterious dark matter that makes up about 27% of the universe's total mass energy content. Primordial black holes, if detected, could offer insights into the universe's first moments, shedding light on the conditions that prevailed during cosmic inflation. Efforts to detect these elusive objects involve studying gravitational lensing, gamma-ray bursts, and the cosmic microwave background for subtle signals of their presence. Observing black holes, challenges and advances. Despite their influence, black holes are notoriously difficult to observe directly. Their defining feature, the event horizon, allows no light or matter to escape, rendering them invisible. However, indirect methods have provided a wealth of information. Observing the orbits of stars near the galactic center, for instance, has revealed the mass and location of supermassive black holes. In 2019, the Event Horizon Telescope, EAT, captured the first ever image of a black hole's shadow, located in the galaxy M87. This image confirmed theoretical predictions and provided a direct glimpse of the warped space-time near the event horizon. Future observations with the EAT and other instruments aim to study black hole accretion disks, magnetic fields, and jet formation in greater detail. Black holes, cosmic architects. Black holes are not merely endpoints of stellar evolution, they are active participants in the cosmic dance, shaping the growth and behavior of galaxies. Their gravitational pull influences the motion of stars, while their feedback processes regulate star formation and gas distribution. Through their interactions with surrounding matter, black holes drive the evolution of galaxies, contributing to the dynamic and ever-changing universe. The study of black holes offers a window into the universe's most extreme conditions, where gravity, space, and time are stretched to their limits. By unraveling their mysteries, we not only learn about the forces that govern galaxies, but also gain deeper insights into the nature of space-time, the evolution of the cosmos, and our place within it. Time and space, the fabric of the universe. Time and space are the foundational dimensions of our universe, intricately woven into the fabric of existence. Albert Einstein's theories of relativity transformed our understanding of these concepts, showing that they are not fixed and independent but interconnected and malleable. Together they form space-time, a dynamic framework influenced by matter, energy, and motion. This revolutionary perspective has reshaped our understanding of the cosmos and the forces that govern it. The nature of space-time. In classical physics, space and time were seen as separate and absolute. Time ticked away uniformly, and space provided a static backdrop for matter in motion. Einstein's special theory of relativity, published in 1905, shattered this notion by demonstrating that time and space are relative, changing depending on the observer's velocity. At the heart of this theory is the concept that the speed of light is constant for all observers, regardless of their motion. This constancy leads to phenomena such as time dilation and length contraction. Time dilation occurs when an object moves close to the speed of light. To an outside observer, time for that object appears to slow down. This effect has been confirmed through experiments with high-speed particles and atomic clocks on fast-moving spacecraft. Length contraction, on the other hand, describes how an object in motion appears shorter along its direction of travel to a stationary observer. Together, these effects show that time and space are not absolute but are interwoven into a single continuum, space-time. Einstein's general theory of relativity, introduced in 1915, expanded on this concept by incorporating gravity into the framework of space-time. In this theory, gravity is not a force acting at a distance, as Isaac Newton proposed, but a curvature in space-time caused by mass and energy. Massive objects, like stars and planets, warp the fabric of space-time, creating the effects we perceive as gravity. This curvature influences the motion of other objects, guiding planets in their orbits and bending the paths of light. Gravity and the warping of space-time. One of the most striking predictions of general relativity is the bending of light by gravity, a phenomenon known as gravitational lensing. When light from a distant object, such as a galaxy, passes near a massive foreground object, the curvature of space-time bends the light, magnifying and distorting the image. Gravitational lensing has become a powerful tool for studying the universe, allowing astronomers to map the distribution of dark matter and observe distant galaxies that would otherwise be too faint to detect. The warping of space-time is also responsible for the slowing of time near massive objects, an effect known as gravitational time dilation. For example, time moves more slowly on the surface of the Earth compared to a satellite in orbit. This effect, though imperceptible in everyday life, is critical for technologies like GPS, which rely on precise timing to provide accurate location data. Without accounting for general relativity, GPS systems would accumulate errors of several kilometers each day. In extreme cases, such as near a black hole, the warping of space-time becomes so intense that time appears to stop entirely for an outside observer. This region, known as the event horizon, marks the boundary beyond which nothing, not even light, can escape. The study of black holes offers a unique window into the interplay of gravity and space-time, testing the limits of general relativity under the most extreme conditions. Space-time and the expansion of the universe. Space-time is not static but dynamic, stretching and evolving with the universe. The discovery that the universe is expanding, first observed by Edwin Hubble in the 1920s, revealed that space itself is growing, carrying galaxies farther apart. This expansion is not caused by galaxies moving through space, but by the stretching of space-time itself. The further away a galaxy is, the faster it appears to recede, a relationship described by Hubble's law. The acceleration of the universe's expansion, driven by dark energy, adds another layer of complexity to the nature of space-time. Dark energy, thought to be a property of space itself, exerts a repulsive force that counteracts gravity on cosmic scales. As space-time expands, new space is created, amplifying the effects of dark energy and accelerating the expansion. This dynamic interplay shapes the large-scale structure of the universe, influencing the distribution of galaxies and clusters. Time, a flexible dimension. Time, often perceived as a linear progression from past to future, is far more complex in the framework of relativity. The concept of simultaneity, events occurring at the same time, is relative, depending on the observer's motion. This means that two observers moving at different velocities may disagree on the order of events, challenging our intuitive understanding of cause and effect. In certain conditions, time can behave in unexpected ways. Near the speed of light, time dilation becomes extreme, allowing travelers to experience significantly less time than those left behind. This effect, known as the twin paradox, has profound implications for interstellar travel, suggesting that journeys to distant stars could be feasible within a human lifetime for the traveler, though centuries might pass on Earth. Theories about time extend beyond relativity, venturing into quantum mechanics and cosmology. Some speculative ideas suggest that time may emerge from deeper physical principles, rather than being a fundamental aspect of reality. Others propose the existence of multiple timelines or the possibility of time travel, though such concepts remain purely theoretical. The unification of space-time and quantum mechanics. One of the greatest challenges in modern physics is reconciling general relativity, which describes gravity and large-scale phenomena, with quantum mechanics, which governs the behavior of particles on the smallest scales. Space-time, as described by relativity, is smooth and continuous, while quantum mechanics operates in a probabilistic realm, where particles exhibit wave-particle duality and uncertainty. The quest for a unified theory, often referred to as quantum gravity, seeks to describe the behavior of space-time at the Planck scale, an incredibly small distance where quantum effects dominate. Theories like string theory and loop quantum gravity offer potential pathways to this unification, suggesting that space-time itself may have a discrete, granular structure at the smallest scales. The mystery of time and space. Time and space remain deeply mysterious, even as our understanding continues to evolve. They are the stage on which the drama of the universe unfolds, shaping everything from the motion of galaxies to the behavior of particles. By studying space-time, we probe the fundamental nature of reality, uncovering the forces that govern existence and the connections that bind the cosmos together. Through the lens of relativity, we see a universe that is dynamic, interconnected, and far stranger than our everyday experiences suggest. Space and time are not mere dimensions, but the very fabric of the cosmos, woven together in ways that challenge our understanding and inspire our imagination. Nebulae, cradles of stars and the beauty of the cosmos. Nebulae are some of the most breathtaking and vital structures in the universe. These vast clouds of gas and dust serve as the birthplaces of stars and planets, as well as the remnants of stellar death. Their vibrant colors and intricate shapes, captured in stunning detail by telescopes like Hubble and James Webb, reveal the dynamic processes at work in the cosmos. Nebulae are not just visually striking, they are laboratories of creation and transformation, shaping the evolution of galaxies and seeding the universe with the ingredients for life. The types of nebulae. Nebulae come in a variety of forms, each representing a different stage in the life cycle of stars. The most common types include emission nebulae. These are glowing clouds of ionized gas, illuminated by the ultraviolet light from nearby young, hot stars. The energy from these stars excites the gas, causing it to emit light in specific wavelengths. The Orion Nebula, one of the most famous emission nebulae, is a stellar nursery where hundreds of new stars are forming. The vibrant reds and pinks in emission nebulae are often due to hydrogen, the most abundant element in the universe. Reflection nebulae. Unlike emission nebulae, reflection nebulae do not emit their own light. Instead, they scatter and reflect the light of nearby stars. This scattering often gives them a bluish appearance, as shorter wavelengths of light are scattered more effectively. The Pleiades star cluster is surrounded by reflection nebulae, adding a ghostly glow to its bright stars. Dark nebulae. These are dense clouds of gas and dust that block the light from stars and other nebulae behind them. Appearing as dark patches against the backdrop of the Milky Way, dark nebulae are regions of concentrated material where star formation may occur. The Horsehead Nebula is a striking example of this type. Planetary nebulae. Despite their name, planetary nebulae have nothing to do with planets. They are the remnants of dying low to medium mass stars, like our Sun. When such a star exhausts its nuclear fuel, it expels its outer layers, leaving behind a glowing shell of gas and a white dwarf at its center. The Ring Nebula and the Helix Nebula are beautiful examples of this phase of stellar evolution. Supernova remnants. These nebulae are the aftermath of a massive star's explosive death. The material ejected during a supernova expands outward, creating complex and colorful structures. The Crab Nebula is a well-studied supernova remnant, its intricate filaments providing clues about the powerful forces at work during the explosion. The role of nebulae in star formation. Nebulae are the cradles of stars, where the interplay of gravity, pressure, and turbulence drives the formation of new stellar systems. Within a nebula, regions of higher density collapse under their own gravity, forming protostars. As these protostars grow, they heat up and begin nuclear fusion, marking their transformation into true stars. The process of star formation is not uniform. Massive stars form more quickly and can influence their surroundings by emitting powerful winds and radiation. These effects carve out cavities in the nebula, compressing nearby gas and triggering the formation of additional stars. This chain reaction of star formation creates clusters, where stars are born in close proximity, sharing a common origin. The material left over after star formation often coalesces into disks around young stars, where planets, moons, and other celestial bodies can form. The study of protoplanetary disks in nebulae provides insights into the early stages of planetary systems, shedding light on the processes that shaped our own solar system. The death of stars and the creation of nebulae. Nebulae are not only the birthplaces of stars but also the remnants of their deaths. When low to medium mass stars, like our Sun, reach the end of their lives, they shed their outer layers, creating planetary nebulae. The remaining core becomes a white dwarf, a dense and slowly cooling stellar remnant. Massive stars, on the other hand, end their lives in supernovae, scattering heavy elements into space. These explosions create supernova remnants, enriching the interstellar medium with the raw materials for future stars and planets. The elements forged in these explosions, such as carbon, oxygen, and iron, are essential for the formation of complex molecules and life. The colors of nebulae. The vivid colors of nebulae are not just beautiful, but also scientifically revealing. They are produced by the emission or reflection of light at specific wavelengths, corresponding to the elements present in the nebula. Hydrogen, the most abundant element, emits a reddish light when ionized. Oxygen often contributes green or blue hues, while other elements like sulfur and nitrogen add to the palette. These colors allow astronomers to study the composition, temperature, and density of nebulae. By analyzing the light from nebulae, scientists can determine their chemical makeup and understand the processes shaping them. Nebulae as laboratories of chemistry. Nebulae are not only composed of hydrogen and helium, but also contain trace amounts of heavier elements and complex molecules. Within their dense regions, chemical reactions occur, forming molecules like water, carbon dioxide, and ammonia. These molecules are often embedded in icy grains of dust, which can survive the harsh conditions of space. The study of molecular clouds' dense regions within nebulae reveals the presence of organic molecules, including those that are precursors to life. These discoveries suggest that the building blocks of life may be widespread in the universe, transported by comets and meteorites to young planets. The role of nebulae in galactic evolution. Nebulae are essential to the life cycle of galaxies, driving star formation and recycling material. As stars are born, evolve, and die, they interact with their surrounding nebulae, enriching them with heavy elements and shaping their structure. This continuous cycle ensures the renewal of galaxies, maintaining their dynamism and diversity. In starburst galaxies, where star formation occurs at an accelerated rate, nebulae are particularly prominent, glowing brightly in ultraviolet and infrared light. These galaxies provide a glimpse into the processes that dominated the early universe, when star formation was at its peak. The legacy of nebulae. Nebulae are more than beautiful phenomena, they are integral to the universe's life cycle. They are the nurseries of stars, the remnants of stellar death, and the reservoirs of the elements that make up planets and life. By studying nebulae, we uncover the interconnected processes that shape galaxies and learn about the origins of our own existence. Each nebula tells a story, a chapter in the grand narrative of the cosmos. Through their study, we deepen our understanding of the forces that govern the universe, gaining a greater appreciation for the beauty and complexity of the cosmos. Interactions shape the structure and evolution of the cosmos, driving processes like star formation, planetary rearrangements, and even the creation of new galaxies. Though they occur over vast timescales, their effects are profound and far-reaching, leaving indelible marks on the universe. Galactic collisions, the dance of titans. Galaxies, the massive collections of stars, gas, dust, and dark matter, often interact and collide in the vast expanse of space. Despite their seemingly isolated positions, gravitational forces can draw them together, triggering a slow and intricate dance that lasts hundreds of millions of years. The Milky Way itself is on a collision course with the Andromeda Galaxy, an event expected to unfold in about 4.5 billion years. During galactic collisions, individual stars rarely collide due to the immense distances between them. Instead, the interaction primarily involves the gas and dust within the galaxies. As these materials are compressed by tidal forces, they ignite bursts of star formation, known as starbursts. These periods of intense activity can produce thousands of new stars, rapidly transforming the colliding galaxies. The gravitational forces at play also warp the shapes of the galaxies, creating spectacular tidal tails, bridges, and loops. The antennae galaxies, a pair of colliding galaxies, showcase these stunning structures, their elongated arms stretching across space as a testament to the power of gravity. Over time, the merging galaxies may settle into a single, larger galaxy, often elliptical in shape. This process, while destructive, is also creative, as it blends the stars, gas, and dark matter of the original galaxies into a new cosmic entity. Planetary collisions, the origins of moons and systems. On a smaller scale, collisions between planets, moons, and other celestial bodies have played a crucial role in shaping planetary systems. Early in the solar system's history, the young planets frequently collided with leftover planetesimals and each other, sculpting their orbits and compositions. One of the most significant planetary collisions is believed to have formed Earth's moon. According to the giant impact hypothesis, a Mars-sized object named Theia collided with the proto-Earth approximately 4.5 billion years ago. The impact ejected vast amounts of debris into orbit, which coalesced to form the Moon. This event not only gave Earth a natural satellite, but also influenced its axial tilt, stabilizing its climate and fostering conditions for life. Collisions also explain the tilted and irregular orbits of some planets and moons in the solar system. Uranus, for example, rotates on its side, likely the result of a massive impact in its early history. These interactions highlight the chaotic and dynamic nature of planetary formation. Star collisions, rare but spectacular. While rare collisions between stars do occur, particularly in densely packed regions like globular clusters, when two stars collide, they merge to form a single, larger star. These collisions can produce unusual objects, such as blue straggler stars that appear younger and hotter than their neighbors because they have been rejuvenated by the influx of material from a collision. In some cases, stellar collisions trigger violent explosions. When a white dwarf in a binary system accretes enough material from its companion star, it can exceed the Chandrasekhar limit, triggering a type Iowa supernova. These explosions are not only spectacular but also serve as important tools for measuring cosmic distances. Cosmic impacts, the shaping of planetary surfaces. Impacts between asteroids, comets, and planets have left visible scars on planetary surfaces, shaping their landscapes and influencing their evolution. The craters on the Moon, Mars, and Mercury are remnants of ancient impacts during the heavy bombardment period, a time when the solar system was teeming with debris. On Earth, impacts have had profound effects on life. The Chicxulub impact, which struck the Yucatan Peninsula 66 million years ago, is widely believed to have caused the mass extinction that wiped out the dinosaurs. This collision released energy equivalent to billions of atomic bombs, creating a global winter that drastically altered the planet's climate. Despite their destructive potential, impacts also bring life-giving materials. Comets and asteroids are thought to have delivered water and organic compounds to the early Earth, playing a crucial role in the origin of life. These icy visitors from the outer solar system carry the building blocks of life, scattering them across the planets they encounter. Gravitational waves, the aftermath of massive mergers. Collisions between compact objects like black holes and neutron stars produce gravitational waves, ripples in the fabric of space-time. Detected by observatories like LIGO and Virgo, these waves provide a new way to study cosmic collisions. In 2017, the merger of two neutron stars was observed not only through gravitational waves but also across the electromagnetic spectrum, marking the dawn of multi-messenger astronomy. These collisions are also the factories of heavy elements like gold, platinum, and uranium. The neutron-rich environment of a neutron-star merger triggers rapid nuclear reactions, creating elements that are scattered into space and incorporated into future stars and planets. The role of collisions in cosmic evolution. Cosmic collisions are not merely destructive, they are engines of transformation and renewal. From the formation of planets and moons to the creation of new galaxies, these interactions drive the evolution of the universe. They redistribute matter and energy, trigger star formation, and enrich the interstellar medium with the elements necessary for life. Observing and studying these collisions provides valuable insights into the processes that shape the cosmos. Advanced simulations and telescopes, such as the James Webb Space Telescope, are uncovering the intricacies of these events, revealing the forces at play in the universe's grand design. Cosmic collisions remind us that the universe is a dynamic and ever-changing place, where destruction often paves the way for creation. These interactions, whether between galaxies, stars, or planets, are part of the intricate web of processes that define the cosmos. By studying them, we gain a deeper understanding of the universe's history, its present state, and its future possibilities. Pulsars and magnetars, the universe's cosmic lighthouses. Among the most fascinating and extreme objects in the universe are pulsars and magnetars, two types of neutron stars that represent the remnants of massive stellar evolution. These dense, compact objects are the size of a city yet contain more mass than the Sun. Their extraordinary properties make them vital laboratories for studying the nature of matter, energy, and the fundamental forces that govern the cosmos. Neutron stars, the origin of pulsars and magnetars. When a massive star exhausts its nuclear fuel, its core collapses under gravity during a supernova explosion. If the remaining core is between 1.4 and 3 times the mass of the Sun, it forms a neutron star. These stars are composed almost entirely of neutrons, held together by the intense force of gravity. A neutron star is incredibly dense. A sugar cube-sized piece of neutron star material would weigh about 1 billion tons on Earth. Their gravitational pull is so strong that they warp the surrounding space-time, creating extreme environments that test the limits of our understanding of physics. Pulsars, rotating beacons in the cosmos. Pulsars are a type of neutron star that emit beams of electromagnetic radiation from their magnetic poles. These beams sweep across the sky as the pulsar rotates, much like the beam of a lighthouse. To an observer on Earth, this creates a periodic signal, pulses of radio waves, visible light, X-rays, or gamma rays, hence the name pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. This object, initially dubbed LEM-1 for Little Green Men, emitted regular pulses every 1.337 seconds, sparking speculation about extraterrestrial signals. Further observations revealed that pulsars are natural phenomena, the remnants of massive stars. Pulsars are incredibly stable, making them precise clocks. Their regular pulses allow scientists to measure time intervals with remarkable accuracy. This stability has led to groundbreaking discoveries, such as the first indirect detection of gravitational waves through the timing of a binary pulsar system. Pulsars have also been used as natural beacons for navigating spacecraft in deep space. Millisecond pulsars, nature's precision instruments. Millisecond pulsars are a subclass of pulsars that rotate hundreds of times per second. These rapid rotations are thought to result from the transfer of angular momentum in a binary system, where a companion star feeds material onto the pulsar, spinning it up to incredible speeds. The extreme stability of millisecond pulsars has enabled the detection of subtle gravitational waves from the merging of supermassive black holes in distant galaxies. Arrays of millisecond pulsars, known as pulsar timing arrays, act as detectors for these low-frequency ripples in space-time, providing insights into the behavior of black holes and the large-scale structure of the universe. Magnetars, the most magnetic objects in the universe. Magnetars are a rare and highly magnetic type of neutron star. Their magnetic fields, up to 1,000 trillion times stronger than Earth's, are the most intense known in the universe. These fields can distort atoms, disrupt nearby electronics, and influence the behavior of space-time itself. Magnetars emit bursts of X-rays and gamma rays, often triggered by starquakes on their surfaces. These quakes occur when the intense magnetic field stresses the star's crust, releasing vast amounts of energy. In 2004, a burst from the magnetar SCRO 180620 released more energy in a fraction of a second than the Sun emits in 100,000 years. If such a burst occurred within a few light years of Earth, it could strip away the planet's atmosphere. The study of magnetars provides a unique opportunity to explore the behavior of matter under extreme magnetic fields. These environments cannot be replicated on Earth, making magnetars natural laboratories for testing the limits of quantum mechanics and the fundamental forces. Binary neutron star systems, sources of gravitational waves. When two neutron stars orbit each other in a binary system, their immense masses and close proximity create a dynamic gravitational interaction. Over time, they lose energy through the emission of gravitational waves, spiraling closer together until they eventually collide. The merger of neutron stars produces powerful gravitational wave signals, as well as electromagnetic counterparts like gamma-ray bursts and kilonovae. These events are key sources of heavy elements such as gold and platinum, created through rapid neutron capture processes during the collision. The observation of a neutron star merger in 2017 marked a historic moment in multi-messenger astronomy, combining gravitational wave and light-based observations to study a single event. Pulsars and magnetars as probes of extreme physics. The extreme environments of pulsars and magnetars offer a window into the laws of physics under conditions that cannot be replicated on Earth. For instance, the densities inside neutron stars are so high that matter exists in exotic states, possibly as a quark gluon plasma or other forms of degenerate matter. Understanding these states could provide insights into the behavior of matter at the smallest scales. The magnetic fields of magnetars challenge our understanding of quantum electrodynamics, QAD, the theory that describes how light and matter interact. In such intense fields, virtual particles can become real, creating effects like vacuum birefringence, where empty space behaves like a prism for light. Pulsars also serve as tools for testing general relativity and alternative theories of gravity. Their precise timing allows scientists to measure tiny changes in their orbits, providing evidence for phenomena like frame dragging, where massive rotating objects twist the fabric of space-time. The future of neutron star research. New telescopes and observatories are poised to revolutionize the study of pulsars and magnetars. Instruments like the Square Kilometre Array, SKA, will dramatically increase the number of known pulsars, improving our understanding of their population and diversity. Space-based observatories, such as NICER, Neutron Star Interior Composition Explorer, are probing the interiors of neutron stars to uncover their mysterious compositions. The detection of gravitational waves from neutron star mergers has opened a new era of discovery, with upcoming detectors like LESA Laser Interferometer Space Antenna, promising to uncover even more signals. These observations will help unravel the mysteries of neutron stars, from their origins to their role in the universe. A legacy of light and magnetism. Pulsars and magnetars are not only remnants of stellar death, but also cosmic beacons and laboratories that illuminate the darkest corners of the universe. Their extreme properties challenge our understanding of physics, offering clues about the nature of matter, energy, and the fundamental forces that shape reality. By studying these enigmatic objects, we gain a deeper appreciation for the interconnected processes that govern the cosmos, from the birth of stars to the creation of heavy elements and the ripples of space-time itself. Pulsars and magnetars remind us that even in the aftermath of destruction, the universe continues to create, inspire, and reveal its secrets. The interstellar medium, the universe's invisible matter. The interstellar medium, ISM, is the vast expanse of gas, dust, and cosmic radiation that exists between the stars and a galaxy. Though it appears empty to the naked eye, the ISM is teeming with activity, serving as the birthplace of stars, the repository of stellar remnants, and the highway for cosmic phenomena. This diffuse medium plays a crucial role in the life cycle of galaxies, connecting the processes of star formation, stellar evolution, and cosmic enrichment. The components of the interstellar medium. The ISM is composed primarily of hydrogen and helium, with trace amounts of heavier elements and dust. These components exist in various phases, determined by temperature and density. Molecular clouds, the coldest and densest regions of the ISM. Molecular clouds are the birthplaces of stars and planets. Temperatures within these clouds can drop to just a few degrees above absolute zero, allowing hydrogen molecules, H2, to form. These clouds, like the famous Orion molecular cloud, harbor the raw materials for star formation and often contain complex organic molecules. Neutral atomic gas. This phase consists of hydrogen atoms, H, in regions with moderate temperatures, 110,000 K. Neutral hydrogen is detected through its characteristic 21 centimeter emission line, a key tool for mapping the structure of galaxies. Ionized gas, found in regions near hot, young stars. Ionized gas, H, emits visible and ultraviolet light. These regions, called HII regions, are glowing clouds of ionized hydrogen, such as the iconic Eagle Nebula's pillars of creation. Interstellar dust. Though it constitutes only about 1% of the ISM's mass, dust plays a critical role in star formation and chemistry. Dust grains, composed of silicates, carbon and ice, shield molecular clouds from ultraviolet radiation, allowing complex molecules to form. Dust also scatters and absorbs light, giving nebulae their distinct colors and obscuring distant stars. Cosmic rays, high-energy particles, primarily protons, traverse the ISM at nearly the speed of light. These cosmic rays originate from supernovae and active galactic nuclei, influencing the chemistry and ionization of the ISM. Star formation in the interstellar medium. The ISM is a dynamic environment shaped by the interplay of gravity, pressure, and turbulence. Star formation begins when molecular clouds collapse under their own gravity, forming dense cores that become protostars. However, the process is far from straightforward. Magnetic fields, turbulence, and feedback from nearby stars can slow or halt collapse, making star formation an inefficient process. Regions of active star formation, such as the Carina Nebula, showcase the complexity of these interactions. Massive stars within these regions emit powerful stellar winds and radiation, carving out cavities in the ISM and triggering the formation of new stars in nearby gas clouds. This feedback mechanism ensures that star formation occurs in cycles, spreading across the galaxy over millions of years. The role of supernovae in the ISM. Supernovae are critical to the evolution of the ISM, injecting energy, enriching it with heavy elements, and driving its dynamic behavior. When a massive star explodes, it ejects vast quantities of material into the ISM, creating a shockwave that compresses surrounding gas. This compression can trigger new star formation, continuing the cycle of stellar birth and death. Supernova remnants, such as the Crab Nebula, are key sites for studying the interaction between supernovae and the ISM. These remnants reveal how energy and material are redistributed, shaping the structure of the ISM on both small and large scales. Interstellar turbulence and magnetic fields. The ISM is far from uniform. It is a turbulent environment where regions of different densities and temperatures coexist. Turbulence plays a key role in regulating star formation, as it creates density fluctuations that can initiate or inhibit gravitational collapse. Magnetic fields thread through the ISM, influencing its dynamics and structure. These fields, though weak compared to those on Earth, are strong enough to shape the motion of gas and dust, guiding the formation of molecular clouds and regulating the efficiency of star formation. Observations of polarized light from dust grains provide insights into the orientation and strength of these magnetic fields. Galactic winds and the ISM.
The ISM is not confined to individual galaxies. It interacts with the intergalactic medium, IGMA, through processes like galactic winds. These winds, driven by supernovae and active galactic nuclei, expel gas and dust into intergalactic space, enriching the IGMA with heavy elements. Galactic winds play a critical role in galaxy evolution, regulating star formation and redistributing material across cosmic scales.
The ISM is a chemical factory. The ISM is a hub of chemical activity where molecules form, interact, and evolve. Dense molecular clouds harbor complex organic molecules, including precursors to amino acids and other building blocks of life. These molecules are protected from harsh radiation by dust grains, which serve as surfaces for chemical reactions. The detection of molecules like water, methanol, and formaldehyde in the ISM highlights its role in the chemistry of the universe. Observations of protoplanetary disks, where planets form, suggest that the chemistry of the ISM influences the composition of planetary systems, potentially delivering the ingredients for life to young planets. The ISM and the Milky Way. In our own Milky Way, the ISM is distributed unevenly, concentrated in the spiral arms and central regions of the galaxy. Observations with telescopes like ALMA, Atacama Large Millimeter Array, and SOFIA, Stratospheric Observatory for Infrared Astronomy, have revealed the intricate structure of the ISM, from massive molecular clouds to diffuse regions of ionized gas. The study of the ISM provides insights into the Milky Way's history and future. By mapping the distribution and motion of gas and dust, astronomers can trace the processes that shape the galaxy, from the formation of spiral arms to the influence of the central supermassive black hole. The future of ISM research. Advances in technology are revolutionizing our understanding of the ISM. Instruments like the James Webb Space Telescope, JWST, are providing unprecedented views of molecular clouds and star-forming regions, revealing the interplay of physics and chemistry in exquisite detail. Future missions, such as the Square Kilometre Array (SKA), will map the distribution of hydrogen across the universe, uncovering the structure of the ISM in distant galaxies. The interstellar medium, though seemingly empty, is a vital component of the cosmos. It connects the life cycles of stars, the evolution of galaxies, and the chemistry of life. By studying the ISM, we uncover the hidden processes that shape the universe, gaining a deeper appreciation for the complexity and interconnectedness of the cosmos. The life cycle of galaxies: formation, evolution, and transformation. Galaxies are the grand architects of the cosmos, vast collections of stars, gas, dust, and dark matter that evolve over billions of years. From their humble beginnings as small proto-galaxies to their majestic forms as spiral, elliptical, or irregular galaxies, their life cycle is shaped by cosmic forces and intricate processes. Understanding the life cycle of galaxies not only reveals the history of the universe, but also illuminates the forces that continue to shape it. The formation of galaxies. The story of galaxies begins in the early universe, a few 100 million years after the Big Bang. During this period, known as the Cosmic Dark Ages, the universe was filled with a nearly uniform distribution of hydrogen and helium gas. Tiny density fluctuations, imprinted during cosmic inflation, served as seeds for galaxy formation. Dark matter played a critical role in this process. Though invisible, it exerted gravitational influence, pulling gas into regions of higher density. These regions collapsed to form the first proto-galaxies, small and irregular clumps of stars and gas. Over time, these proto-galaxies merged and accreted material, growing into the massive galaxies we see today. The first stars within these galaxies, known as population II stars, were massive and short-lived. Their supernova explosions enriched the surrounding gas with heavy elements, allowing for the formation of more complex molecules and the birth of new generations of stars. Galaxy classification: spirals, ellipticals, and irregulars. Galaxies are classified into three main types based on their structure. Spiral galaxies, characterized by a central bulge surrounded by flat, rotating disks of stars and gas. Spiral galaxies often have distinct arms where star formation is active. The Milky Way and Andromeda are prime examples. These galaxies are rich in gas and dust, fueling ongoing star formation. Elliptical galaxies: these galaxies have a more spherical or elongated shape and lack the defined structure of spirals. They contain older, redder stars and have little gas or dust, indicating that star formation has largely ceased. Elliptical galaxies often form through the mergers of smaller galaxies. Irregular galaxies, lacking a distinct shape. Irregular galaxies are often the result of gravitational interactions or collisions. These galaxies are rich in gas and dust, making them active sites of star formation. Galaxy evolution: growth and interaction. Galaxies evolve through a combination of internal processes and external influences. Internally, star formation, supernovae, and black hole activity shape their structure and composition. Externally, interactions with other galaxies and the intergalactic medium drive significant changes. Mergers and collisions: galaxy mergers are among the most transformative events in their evolution. When two galaxies collide, their stars pass through each other, but their gas and dust interact, triggering bursts of star formation. Over time, the merging galaxies may settle into a new, larger structure, often becoming elliptical galaxies. The Milky Way's future merger with Andromeda will likely result in a new galaxy, sometimes referred to as Milkomeda. Observations of colliding galaxies, such as the antennae galaxies, provide a glimpse into the dynamic processes at play. Galactic cannibalism: larger galaxies often grow by consuming smaller ones in a process called galactic cannibalism. The gravitational pull of the larger galaxy disrupts and absorbs the smaller galaxy, adding its stars, gas, and dark matter to the larger system. This process contributes to the growth of massive elliptical galaxies. Starburst galaxies: in some cases, interactions or internal processes lead to periods of intense star formation, creating starburst galaxies. These galaxies burn through their gas rapidly, producing large numbers of new stars over a relatively short period. The role of supermassive black holes in galaxy evolution. At the center of nearly every massive galaxy lies a supermassive black hole, whose mass is often millions or billions of times that of the Sun. These black holes influence their host galaxies through feedback processes, such as jets of high-energy particles and radiation emitted during active phases. When a supermassive black hole accretes matter, it powers an active galactic nucleus, AGN, emitting enormous amounts of energy. This energy can heat or expel gas, regulating star formation and shaping the galaxy's evolution. The relationship between a galaxy's central black hole and its properties, such as the M-sigma relation, highlights the interconnected growth of galaxies and their black holes. Galactic quenching: the end of star formation. Galaxies do not form stars indefinitely. Over time, processes such as feedback from black holes, supernovae, and the depletion of gas reservoirs can halt star formation, transforming galaxies into quiescent systems. This transition, known as quenching, marks a significant phase in a galaxy's life cycle. Quenching can be triggered by feedback processes. Energy from AGNs and supernovae can heat or expel gas, preventing it from cooling and forming new stars. Galaxy mergers. The chaotic interactions during mergers can disrupt gas reservoirs, shutting down star formation. Environmental effects. Galaxies in dense clusters experience ram pressure stripping, where their gas is removed by the surrounding intergalactic medium, leading to quenching. Quiescent galaxies, often elliptical in shape, continue to evolve slowly, their stars aging and cooling over billions of years. The intergalactic medium and galactic recycling. The intergalactic medium, IGM, the diffuse gas between galaxies, plays a vital role in their life cycle. Galaxies accrete gas from the IGM to fuel star formation, while feedback processes return enriched material to the IGM, creating a cycle of matter and energy exchange.
This galactic recycling enriches the universe with heavy elements, spreading the building blocks of stars, planets, and life. Observations of the AIM using telescopes like the James Webb Space Telescope, JWST, are revealing the complex interactions between galaxies and their environments.
The future of galaxies. As the universe continues to expand, galaxies will evolve in new and fascinating ways. Over billions of years, the accelerating expansion driven by dark energy will isolate galaxies from one another, as the space between them grows faster than the speed of light. In this distant future, galaxies like the Milky Way will become island universes, isolated in the vast emptiness of space. Internally, galaxies will slowly fade as star formation ceases and existing stars burn out. White dwarfs will cool into black dwarfs, and black holes will dominate the remnants of galactic cores. The ultimate fate of galaxies depends on the nature of dark energy and the universe's long-term evolution, whether through a big freeze, big rip, or other scenarios. Galaxies, the dynamic engines of the universe. Galaxies are more than collections of stars and matter. They are dynamic engines that drive the evolution of the universe. Their interactions, growth, and transformations reflect the forces that shape the cosmos, from gravity and dark matter to black holes and interstellar chemistry.
By studying galaxies, we unravel the history of the universe, exploring its past, present, and future. From their brilliant clusters of stars to their hidden dark matter halos, galaxies remind us of the intricate and interconnected processes that govern the cosmos, offering a window into the vast and ever-changing universe.
The intergalactic medium, the universe's vast and mysterious expanse. Between the luminous beacons of galaxies lies the intergalactic medium, IGM, a vast and tenuous expanse of gas, plasma, and dark matter. While it may seem empty, the IGM is a critical component of the cosmos, serving as the connective tissue of the universe and a key player in its evolution. This medium provides a bridge between galaxies, influencing their growth, interactions, and the large-scale structure of the universe. The composition of the intergalactic medium. The IGM consists primarily of hydrogen and helium, the two lightest and most abundant elements, formed in the first few minutes after the Big Bang during primordial nucleosynthesis. Trace amounts of heavier elements, known as metals in astrophysical terms, are also present, enriched by supernovae and galactic winds.
The IGM exists in different states, depending on its temperature and density.
The warm-hot intergalactic medium, WIM. This phase is composed of gas at temperatures ranging from 10,000 to 10 million Kelvin. It is thought to contain a significant fraction of the universe's baryonic matter, much of which remains hidden in observations due to its diffuse nature. Ionized gas, most of the IGM is ionized, meaning its hydrogen and helium atoms have been stripped of electrons. This ionization occurred during two key epochs. Rhyonisation, about 500 million years after the Big Bang. The first stars and galaxies emitted tense ultraviolet radiation, reionizing the neutral hydrogen left over from recombination. Helium reionization. Occurring later, this process was driven by the energetic radiation from quasars, reionizing helium and heating the IGM further.
Lyman alpha forest. The IgM's neutral hydrogen is detectable through absorption lines in the spectra of distant quasars. These lines, known as the Lyman alpha forest, provide a detailed map of the IgM's distribution, temperature, and composition.
The IgM's role in cosmic structure formation. The IgM is a vital component of the cosmic web, the large-scale structure of the universe. Gravity pulls the gas into filaments that connect galaxies and clusters, creating a network of interconnected structures spanning hundreds of millions of light years. Observations and simulations show that the IgM traces the distribution of dark matter, which serves as the scaffolding for this cosmic web. As galaxies form and grow, they accrete gas from the IgM along these filaments. This infall of material fuels star formation and contributes to the growth of supermassive black holes. The interplay between galaxies and the IgM ensures the continuous recycling of matter and energy, maintaining the dynamism of the universe.
Galactic feedback in the IgM.
Galaxies influence the IgM through feedback processes driven by supernovae, stellar winds, and active galactic nuclei (AGN). These processes inject energy and metals into the surrounding medium, enriching the IgM and affecting its thermal state. For example,
Supernova feedback. The explosion of massive stars releases shockwaves that heat and expel gas from galaxies. This gas mixes with the IgM, spreading heavy elements like carbon, oxygen, and iron.
AGN feedback. Jets and outflows from supermassive black holes can heat the IgM, preventing gas from cooling and falling back into galaxies. This process regulates star formation and shapes the large-scale distribution of gas. The enrichment of the IgM with metals provides valuable information about the history of star formation and galactic evolution. Observations of the IgM's metallicity using X-ray and ultraviolet telescopes reveal the cumulative effects of billions of years of feedback. The missing baryon problem and the IgM. For decades, astronomers faced the missing baryon problem, where the observed amount of ordinary matter in the universe fell short of theoretical predictions. The solution to this mystery lies in the IgM, specifically the WIM. Observations of the WIM through X-ray emissions and absorption lines in quasar spectra have accounted for the missing baryons, confirming that much of the universe's ordinary matter resides in this diffuse medium. The study of the WIM is challenging due to its faint signals, but advances in telescope technology, such as the Chandra X-ray Observatory and the upcoming Athena mission, are providing increasingly detailed insights into this elusive component of the universe. The IgM and the epoch of reionization.
The IgM played a central role during the epoch of reionization, a transformative period when the first stars and galaxies ionized the universe's neutral hydrogen. This era marked the end of the cosmic dark ages and the beginning of visible structures in the universe.
Observations of reionization are made possible by studying the CMB, the Lyman alpha forest, and high redshift galaxies. These data reveal the timeline of reionization and the sources of the ultraviolet radiation responsible for it. Understanding this epoch sheds light on the formation of the first galaxies and the early evolution of the IgM. Intergalactic medium as a laboratory for fundamental physics. The IgM is an ideal environment for testing theories of fundamental physics. Its diffuse nature and vast scales provide a unique laboratory for studying dark matter. The IgM traces the distribution of dark matter, offering indirect evidence of its presence and properties. Simulations of the cosmic web, based on dark matter dynamics, align closely with observations of the IgM. Cosmic magnetism. The magnetic fields threading the IgM are poorly understood but could offer insights into their origin, evolution, and impact on galaxy formation. Neutrinos and cosmic rays. High-energy particles from cosmic sources propagate through the IgM, providing information about their origins and interactions with the medium. Future studies of the intergalactic medium. The next generation of observatories promises to revolutionize our understanding of the IgM. Instruments like the James Webb Space Telescope, JWST, and the European Space Agency's Euclid mission are exploring the IgM's role in cosmic structure formation and evolution. At the same time, X-ray and radio telescopes are probing the WIM and its interactions with galaxies. Simulations of the IgM using supercomputers and advanced algorithms are also advancing our knowledge. These simulations recreate the formation and evolution of the cosmic web, helping scientists interpret observations and refine models of the universe's growth.
The IM, the universe's vast interconnection.
The intergalactic medium is more than the space between galaxies, it is the fabric that connects them, driving the processes that shape the cosmos. By studying the IGM, we uncover the hidden dynamics of the universe, from its earliest moments to its current structure. Through its interplay with galaxies, the IGM ensures the continuous cycle of matter and energy, enriching the cosmos and enabling the formation of stars, planets, and life. It is a reminder that even the seemingly empty regions of space are filled with activity, contributing to the grand tapestry of the universe. Cosmic inflation, the universe's explosive beginning. Cosmic inflation is one of the most groundbreaking concepts in modern cosmology, offering a solution to many of the mysteries surrounding the early universe. This rapid and exponential expansion, theorized to have occurred within the first fraction of a second after the Big Bang, provides a framework for understanding the universe's uniformity, structure, and vastness. Although it lasted for an almost unimaginably short time, its effects have shaped the cosmos as we observe it today. The origins of inflation theory. The theory of inflation was first proposed in the early 1980s by physicist Alan Guth as a modification to the standard Big Bang model. The Big Bang theory explained the universe's expansion and the formation of elements, but left several key questions unanswered. The Horizon Problem, observations of the cosmic microwave background, CMB, reveal that the universe is remarkably uniform in temperature across vast distances. However, regions of the CMB are so far apart that they could not have exchanged information or energy under standard Big Bang conditions. The flatness problem. The observable universe appears to be spatially flat, meaning that its geometry is neither curved nor open. Achieving such a balance requires finely tuned initial conditions, which seemed implausible. The monopole problem. Grand unified theories, GUTs, predicted the existence of magnetic monopoles, hypothetical particles with a single magnetic pole. However, these have never been observed, suggesting something suppressed their production or abundance. Inflation addressed these problems by positing that the universe underwent a brief but extreme expansion, growing exponentially in size. This expansion stretched and smoothed out any initial irregularities, creating the uniform and flat cosmos we see today, while diluting unwanted relics like monopoles. How inflation worked. Inflation is thought to have been driven by a scalar field, often called the inflaton field. This field had a high potential energy density, which acted like a repulsive force, causing space itself to expand exponentially. During this phase, the universe doubled in size repeatedly, expanding by a factor of at least 102. 61026 in less than 103 21032 seconds. Eventually, the inflaton field transitioned to a lower energy state, releasing its stored energy in a process known as reheating. This energy was converted into particles and radiation, kickstarting the standard Big Bang phase and setting the stage for the universe's continued evolution. The imprints of inflation. Inflation left observable imprints on the universe that provide strong evidence for its occurrence. Cosmic microwave background, CMB. The CMB is a snapshot of the universe when it was just 380,000 years old. Tiny fluctuations in its temperature correspond to variations in density, seeded by quantum fluctuations during inflation. These variations later grew into the large-scale structures of galaxies and clusters. Large-scale structure. The distribution of galaxies and galaxy clusters aligns with the patterns predicted by inflation. These structures form a cosmic web that reflects the amplified quantum fluctuations stretched during the inflationary epoch. Primordial gravitational waves. Inflation would have generated ripples in space-time, known as primordial gravitational waves. While these waves have not yet been directly detected, they may be observable as subtle polarization patterns in the CMB. The quantum origins of structure. One of inflation's most remarkable implications is that the universe's large-scale structure originated from quantum fluctuations. During inflation, these fluctuations in the inflaton field were stretched to macroscopic scales, creating regions of slightly different densities. These differences acted as the seeds for the formation of stars, galaxies, and clusters. The idea that quantum mechanics, a theory governing the microscopic world, could influence the structure of the entire cosmos highlights the deep interconnectedness of physics across scales, variants, and extensions of inflation. While the basic idea of inflation is widely accepted, many variants and extensions have been proposed, each offering different mechanisms or implications. Chaotic inflation. This model suggests that inflation began in a chaotic state, with the inflated field taking on random values across the universe. Eternal inflation. In this scenario, inflation never completely ends in certain regions of the universe. Instead, pockets of space transition out of the inflationary phase, creating bubble universes that could form a multiverse. Hybrid inflation. This model involves multiple fields interacting to drive inflation and end it, offering a richer framework for exploring the dynamics of the early universe. Each of these models provides a different perspective on the nature of inflation and its potential connections to other areas of physics, such as string theory and quantum gravity. Challenges and open questions. Despite its successes, inflation is not without challenges. The inflated field. While inflation requires a scalar field, the exact nature of the inflaton remains unknown. Determining its properties and origin is a major focus of theoretical physics. Initial conditions. Inflation assumes certain initial conditions, such as a pre-existing universe. Understanding why these conditions existed is a profound question.
Fine-tuning. Some parameters in inflation models require fine-tuning, leading to debates about whether inflation is the most natural explanation.
Ongoing research, including experiments designed to detect primordial gravitational waves and refine measurements of the CMB, aims to address these questions and test the predictions of inflationary models. Inflation's role in cosmic evolution. Inflation is more than just a phase of rapid expansion. It is the foundation of our understanding of the universe's earliest moments. By smoothing out irregularities, seeding structure, and explaining the universe's flatness and uniformity, inflation provides a coherent framework for the cosmos we observe. Moreover, inflation connects cosmology with fundamental physics, bridging the macroscopic and quantum realms. It offers clues about the unification of forces, the nature of space-time, and the origins of the universe itself. The legacy of inflation. Cosmic inflation represents one of the most profound shifts in our understanding of the universe. It explains how the cosmos transitioned from a quantum state to the vast and structured expanse we see today. Its predictions have been confirmed by decades of observations, yet its mysteries continue to inspire exploration. As new technologies and theories emerge, the study of inflation will remain at the forefront of cosmology, revealing the secrets of the universe's beginning and its potential futures. Inflation reminds us that even the briefest moments in cosmic history can have lasting and transformative effects, shaping the universe on the grandest scales. Dark matter. The universe's hidden framework. Dark matter is one of the most mysterious and vital components of the universe, comprising about 27% of its total mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Yet its presence is undeniable, inferred through its gravitational effects on galaxies, clusters, and the large-scale structure of the cosmos. Understanding dark matter is a central challenge in modern physics and cosmology, promising to unlock the secrets of the universe's composition and evolution. The evidence for dark matter.
The existence of dark matter was first proposed in the early 20th century to explain discrepancies between the observed and expected behavior of galaxies and clusters. Key pieces of evidence include
galaxy rotation curves. Observations of spiral galaxies reveal that their outer regions rotate at much higher speeds than expected based on visible matter alone. This suggests the presence of an unseen mass providing additional gravitational pull. Galaxy clusters. In the 1930s, Fritz Zwicky studied the Coma cluster and found that its galaxies were moving too quickly to be held together by their visible mass. He coined the term dark matter to describe the missing mass needed to explain this phenomenon.
Gravitational lensing, the bending of light by massive objects, as predicted by Einstein's general relativity, provides a direct measure of mass distribution. Studies of galaxy clusters show that their total mass far exceeds what can be accounted for by visible matter alone.
Cosmic microwave background, CMB. The patterns in the CMB, a relic of the early universe, are shaped by the interplay of ordinary matter, and dark energy. Observations of the CMB, such as those from the Planck satellite, confirm that dark matter is a significant component of the universe. Large-scale structure. The distribution of galaxies and clusters in the cosmic web matches simulations that include dark matter. Without it, the observed structure could not have formed within the universe's 13.8 billion-year history. The nature of dark matter. While the existence of dark matter is well supported, its nature remains elusive. Several theories propose what dark matter might be. Weakly interacting massive particles, WIMPs. These hypothetical particles interact only through gravity and the weak nuclear force. WIMPs have been a leading candidate for decades, with experiments like Lux-Zeppelin and Xenon-1T searching for their interactions with ordinary matter. Actions, extremely light particles predicted by extensions of the Standard Model. Actions could solve several outstanding problems in particle physics and serve as a dark matter candidate. Their detection is pursued through experiments like ADMEX, which search for their conversion into photons and magnetic fields. Sterile neutrinos. These particles are a proposed extension of the known neutrinos. They interact even more weakly than ordinary neutrinos and could account for the dark matter. Mayachus. Massive astrophysical compact halo objects, such as black holes, neutron stars, or rogue planets, were once considered as dark matter candidates. However, observations show they cannot account for the required mass. Self-interacting dark matter, SIB. This theory suggests that dark matter particles interact with each other, explaining certain observations in galaxy cores that WIMPs cannot. Dark matter's role in cosmic evolution. Dark matter is the scaffolding of the universe, shaping the formation and evolution of galaxies, clusters, and the cosmic web. Its gravitational pull allowed small density fluctuations in the early universe to grow into the large-scale structures we see today. Without dark matter, ordinary matter would not have clumped together to form stars, galaxies, and planets within the universe's lifetime. In galaxy clusters, dark matter dominates the total mass, binding galaxies together and influencing their motions. It also prevents the hot gas in clusters from escaping, allowing for the formation of stars over billions of years. The search for dark matter. Scientists use a variety of methods to detect and study dark matter. Direct detection. Experiments like Lux-Zeppelin and Pandax aim to detect dark matter particles colliding with atomic nuclei in ultra-sensitive detectors. These experiments are placed deep underground to shield them from cosmic rays and background radiation. Indirect detection. Telescopes search for signals of dark matter annihilation or decay, such as gamma rays, neutrinos, or cosmic rays. The Fermi Gamma Ray Space Telescope, for example, observes regions like the galactic center, where dark matter density is thought to be high. Collider experiments, particle accelerators, such as the Large Hadron Collider, LHC, search for evidence of dark matter production in high-energy collisions. If dark matter particles exist, they might be created and detected indirectly through missing energy in particle interactions. Astrophysical observations, studies of galaxy rotation curves, gravitational lensing, and the CMB provide indirect evidence of dark matter and help refine theoretical models. Simulations. Advanced cosmological simulations, such as the Illustris and Millennium projects, model the behavior of dark matter in the universe, comparing predictions with observations. Challenges and controversies. Despite decades of effort, dark matter has not been directly detected, leading to alternative theories. Modified gravity, MUNDI. Some physicists propose that dark matter effects could instead be explained by modifying the laws of gravity at large scales. While MUND can explain certain observations, it struggles to account for others, such as the CMB. Primordial black holes. Recent studies suggest that dark matter might consist of primordial black holes formed shortly after the Big Bang. This idea has gained traction with the detection of gravitational waves from black hole mergers, but it remains speculative. Emergent gravity. Theoretical physicist Eric Verlinde has proposed that gravity itself may emerge from the entropy of the universe, eliminating the need for dark matter. This idea is still in its infancy and requires further development. The future of dark matter research. The quest to understand dark matter is entering a new phase with advances in technology and theory. Upcoming experiments, such as the European Space Agency's Euclid mission and the Vera C. Rubin Observatory, will map the distribution of dark matter with unprecedented precision. Meanwhile, particle physics experiments continue to push the boundaries of detection, exploring new parameter spaces. The search for dark matter is not just about solving a cosmic mystery. It is a journey to understand the universe's most fundamental components. By uncovering the nature of dark matter, scientists hope to reveal deeper connections between gravity, quantum mechanics, and the origins of the cosmos. Dark matter, the invisible architect.
Dark matter remains one of the greatest enigmas in science. Its unseen presence shapes the universe, influencing the formation of galaxies, clusters, and the cosmic web. Though invisible, its effects are written across the cosmos, offering clues to its nature and role.
As scientists delve deeper into the mysteries of dark matter, they are not only seeking to complete the picture of the universe's composition, but also to uncover new physics that could transform our understanding of reality itself. Dark matter reminds us that even in the absence of light, the universe's most profound secrets continue to beckon. Dark energy, the force driving the universe's accelerated expansion. Dark energy is perhaps the most perplexing phenomenon in modern cosmology, accounting for approximately 68% of the universe's total energy density. Unlike dark matter, which binds galaxies together with its gravitational pull, dark energy acts as a repulsive force, driving the accelerated expansion of the universe. Its discovery in the late 1990s fundamentally altered our understanding of the cosmos, raising profound questions about its nature, origin, and implications for the universe's ultimate fate. The discovery of dark energy. The existence of dark energy was first inferred through observations of Type Iowa supernovae exploding stars that serve as standard candles for measuring cosmic distances. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, found that distant supernovae appeared dimmer than expected. This indicated that the universe's expansion was not slowing down due to gravity, as previously thought, but accelerating.
This surprising result was soon corroborated by other lines of evidence, including measurements of the cosmic microwave background, CMB, and the large-scale distribution of galaxies. These findings required a new component in the universe's energy budget, dark energy.
The nature of dark energy. Despite its dominance in the universe, the nature of dark energy remains elusive. Several theories have been proposed to explain its properties. The cosmological constant, first introduced by Albert Einstein as a term in his equations of general relativity, the cosmological constant represents a constant energy density inherent to space itself. In this model, dark energy does not change over time and is consistent with observations of the universe's accelerated expansion. Quintessence. Unlike the cosmological constant, quintessence posits that dark energy is a dynamic field that evolves over time. This scalar field would vary in strength and density, potentially explaining subtle discrepancies in observational data. Modified gravity. Some theories suggest that the effects attributed to dark energy could instead arise from modifications to general relativity on cosmic scales. These models propose new laws of gravity that could account for the observed acceleration. Extra dimensions. Theories based on string theory or other frameworks propose that dark energy may be a manifestation of additional spatial dimensions beyond the familiar three. These dimensions could influence the expansion of the universe in unexpected ways. Vacuum energy. Quantum field theory suggests that even empty space is filled with vacuum energy from virtual particles. While this idea aligns with the concept of the cosmological constant, theoretical calculations of vacuum energy density differ dramatically from observations, highlighting a major unresolved problem. The effects of dark energy on the universe. Dark energy's influence extends across the cosmos, shaping its past, present, and future. Accelerated expansion. Dark energy counteracts gravity, causing the expansion of space to accelerate. This effect is most pronounced on large scales, where gravitational forces are weaker. Large-scale structure. By driving galaxies apart, dark energy affects the growth of cosmic structures. Over time, it suppresses the formation of new galaxies and clusters, creating a more isolated universe. The geometry of the universe. Observations of the CMB show that the universe is spatially flat, a result consistent with the influence of dark energy. This flatness requires a precise balance between dark energy, dark matter, and ordinary matter. Cosmic fate. Dark energy plays a crucial role in determining the universe's ultimate destiny. If its strength remains constant, the universe will continue expanding indefinitely in a scenario known as the Big Freeze. If its strength increases, it could lead to a big rip, tearing apart galaxies, stars, and even atoms. Observing and measuring dark energy. The study of dark energy relies on precise measurements of cosmic expansion and structure formation. Key observational techniques include supernova surveys. Observing type Iowa supernovae at different redshifts provides a direct measure of the universe's expansion history. Projects like the Dark Energy Survey (DS) and the Vera C. Rubin Observatory aim to identify thousands of supernovae to refine these measurements. Baryon acoustic oscillations, BAOs. These are ripples in the distribution of galaxies caused by sound waves in the early universe. BAOs serve as standard rulers for measuring cosmic distances and the effects of dark energy. Gravitational lensing. The bending of light by massive objects reveals the distribution of matter and the influence of dark energy on structure formation. Weak gravitational lensing, in particular, provides insights into the growth of cosmic structures. Cosmic microwave background, CMB. Detailed measurements of the CMB, such as those made by the Planck satellite, constrain the energy density and properties of dark energy. Galaxy clustering. By studying the distribution and clustering of galaxies, astronomers can infer the effects of dark energy on large-scale structure. Challenges in understanding dark energy. Despite extensive research, dark energy remains one of the most significant enigmas in science. Key challenges include theoretical framework. Developing a consistent theoretical framework that integrates dark energy with quantum mechanics and general relativity is an ongoing challenge. Vacuum energy discrepancy. The discrepancy between the observed and predicted vacuum energy density off by a factor of 101. 201, 0121, 120 is one of the greatest unsolved problems in physics. Evolution of dark energy. Determining whether dark energy is constant or dynamic requires precise observations over cosmic time. Distinguishing models. The subtle differences between competing models of dark energy, such as the cosmological constant and quintessence, are difficult to distinguish observationally. The future of dark energy research. Upcoming missions and technologies promise to shed new light on dark energy. Euclid mission. This European Space Agency mission will map the geometry of the universe with unprecedented precision, focusing on dark energy and dark matter. Nancy Grace Roman Space Telescope. NASA's next-generation telescope will study dark energy through wide-field imaging and supernova surveys. Next-generation cosmological simulations. Advanced simulations will model the effects of dark energy on cosmic structure, helping to interpret observational data. Quantum gravity theories. Efforts to unify quantum mechanics and general relativity may provide insights into the nature of dark energy. Dark energy. The universe's invisible architect. Dark energy is not just a mystery, it is a window into the fundamental nature of the cosmos. By driving the universe's expansion and shaping its structure, dark energy challenges our understanding of space, time, and gravity. Its study pushes the boundaries of physics, linking cosmology with quantum mechanics and the search for a unified theory. As scientists unravel the secrets of dark energy, they are not only probing the forces that govern the universe, but also redefining our place within it. Dark energy reminds us that even the unseen can shape the cosmos in profound and unexpected ways, offering a glimpse into the infinite complexity of the universe. The multiverse, exploring the possibility of infinite universes. The concept of the multiverse, the idea that our universe is just one of many, has fascinated scientists and philosophers alike. While it may seem like the realm of science fiction, the multiverse hypothesis arises naturally from several areas of modern physics and cosmology. If true, it could fundamentally reshape our understanding of reality, offering answers to some of the most profound questions about existence, fine-tuning, and the nature of space and time. Origins of the multiverse hypothesis. The idea of multiple universes has ancient roots in philosophical speculation, but its modern scientific foundation comes from theories in physics and cosmology. Several lines of inquiry suggest the possibility of a multiverse. Cosmic inflation, the rapid expansion of space during the inflationary epoch, could create separate bubble universes. In this model, different regions of space-time stop inflating at different times, forming distinct universes with varying physical properties. This concept, known as eternal inflation, predicts an infinite number of bubble universes. Quantum mechanics. The many worlds interpretation of quantum mechanics posits that every quantum event spawns new branches of reality. In this framework, the multiverse consists of an infinite number of parallel universes, each representing a different outcome of quantum events. String theory. In string theory, the fundamental nature of reality is described by tiny, vibrating strings. The theory predicts a vast landscape of possible solutions, each corresponding to a universe with its own set of physical laws. This landscape could account for the apparent fine-tuning of our universe's constants. Brain cosmology. In some versions of string theory, our universe exists on a three-dimensional brain within a higher dimensional space. Other brains, potentially hosting their own universes, could exist parallel to ours, separated by dimensions we cannot perceive. Evidence and observational challenges. Direct evidence for the multiverse is difficult to obtain because, by definition, other universes are separate and may not interact with ours. However, indirect clues and theoretical motivations make the concept compelling. Cosmic microwave background, CMB, tiny anomalies or patterns in the CMB could suggest interactions between our universe and others. For instance, cold spots in the CMB might be remnants of collisions with other bubble universes. Fine-tuning of physical constants. The precise values of the fundamental constants, such as the strength of gravity and the charge of the electron, allow for the existence of life in the universe as we know it. The multiverse provides a potential explanation. If countless universes exist, each with different constants, we find ourselves in one of the few that supports life. Mathematical consistency. The multiverse arises naturally from theories like eternal inflation and string theory, lending it theoretical support even in the absence of direct evidence. Quantum interference. While the many worlds interpretation of quantum mechanics cannot be directly tested, its predictions align with observed phenomena like interference patterns in the double-slit experiment. Types of multiverses. Not all multiverse theories are the same. Different frameworks propose varying structures and relationships between universes. Level I multiverse. In this model, based on cosmic inflation, the universe is infinitely large and uniform. Regions beyond our observable horizon may differ due to random initial conditions, effectively forming separate universes. Level I multiverse. Eternal inflation predicts distinct bubble universes with different physical constants and properties. These universes are causally disconnected from each other. Level I multiverse. The many worlds interpretation of quantum mechanics suggests that all possible outcomes of quantum events are realized in separate branches of reality. Level IV multiverse, proposed by physicist Max Tegmark. This idea posits that all mathematically consistent structures exist as physical realities, encompassing every conceivable universe. Philosophical and scientific implications. The multiverse raises profound questions about the nature of reality and our place within it. Anthropic principle. The multiverse lends support to the anthropic principle, which states that we observe the universe to be fine-tuned for life, because only such a universe allows observers to exist. In a multiverse, life-friendly universes are just a small subset of the whole. Redefining reality. If other universes exist, our understanding of everything must expand to include a potentially infinite set of realities. Falsifiability. Critics argue that the multiverse is unscientific because it may not be directly testable. Proponents counter that indirect evidence and theoretical consistency provide a solid foundation for the hypothesis. Ultimate origins. The multiverse does not necessarily solve the question of ultimate origins. Instead, it shifts the focus to the mechanism that generates the multiverse itself, raising deeper questions about the nature of existence. The future of multiverse research. While direct observation of other universes remains beyond current capabilities, advancements in technology and theory may provide new insights. Cosmic microwave background (CMB) studies, detailed measurements of the CMB, could reveal subtle imprints of interactions with other universes. Particle physics, discoveries in high-energy physics, such as evidence for extra dimensions or new fundamental particles, could provide indirect support for multiverse theories. Quantum computing. Exploring the many worlds interpretation of quantum mechanics could deepen our understanding of branching realities. Gravitational wave astronomy. Collisions between bubble universes, if they occurred, might leave detectable signatures in the form of gravitational waves. The multiverse, infinite possibilities. The multiverse hypothesis invites us to imagine a cosmos far richer and more varied than we ever thought possible. It challenges our notions of uniqueness and encourages us to rethink the boundaries of science and philosophy. Whether or not the multiverse is real, the exploration of this idea pushes the limits of human understanding, inspiring us to ask bold questions about the nature of existence and the infinite possibilities that may lie beyond.